So we can start like a minute late or so just to give people a chance to come. This session is a little longer. It's 5 talks instead of the others, but we have 15 extra minutes, so there's a little bit of extra time. Cool.
Okay, good morning, everyone. Welcome to session 3 of ITC 2020. Our first speaker, our first session, this is the first session of the morning, and I will let the session chairs lead the session.
Hi, I'm Xiao. Let me give a brief
Xiao, you're
introduction.
muted.
Mute myself.
We can hear you,
We
Xiao,
can
now.
hear you.
You can or you cannot?
You're good.
My mistake, sorry, go ahead.
Okay, sorry. Okay, so I only have 3 to 5 minutes, maybe now it's already late. Okay, so hi everyone, I'm Xiao. Let me give a brief introduction. So there are a lot of talks in this section. We have 5 talks. And if you stare at them, you will quickly find some common thing. So the first thing to notice is that the first 3 talks about secret sharings. And the next thing to notice is the next 2 talks about codes. So that's why this section is called secret sharing and codes. Okay, we have 5 talks. I tried my best to try to group them. So eventually I get 3 collections I would like to share with you. So let me describe those collections. the first collection of the talks. To introduce a little bit about background, I need to mention, in the area of secret sharing, one of the major open problems is to determine what's the optimal share size for general access structures. Even we have spent a lot of efforts, the current best constructions to share even a single bit secret, everybody needs to get exponential number of share bits. Is this exponential number of bits necessary? Unfortunately, we don't know. So the best lower bound we get is not even linear. So there is an exponential gap between upper bound and the lower bounds. Closing this gap is perhaps the most one of the most important problem in this area. So in today's invited talk, you're going to hear exciting progress in improving the upper bounds. Besides invited talks, although the situation for general schemes are really bad, we have important special cases which the situation is exponentially better. In particular, there's a subclass of general schemes called linear schemes. So for those schemes, we can prove exponential lower bounds. Then a natural question to ask is what happened in between? So we know a lot about linear schemes. For general schemes, like the lower bounds really bad, is there any way to brought ideas from linear to general schemes? Is there any notion in between them? So in the third talk of this section, you're going to hear about polynomial secret sharing schemes, try to bridge this gap. Another special case of general access structure is called threshold access structure. So usually, even the construction for general access structure is really bad, but we have very good construction for threshold cases. Is there any chance we can also define some intermediate notion, try to broad ideas from threshold cases, try to improve the general cases? So in the first talk, you're going to hear some approaches, try to bridge these two. So to sum up, the first collections is all about bridging gaps. So we have exponential gaps between different kinds of notion, upper and lower bounds, special case and general case. We try to define intermediate notions, try to gain understanding slowly. Hopefully we can get help to attack the difficult problems. Okay, so this is the first collection. Let me go with the second collection. So the second collection contains two talks. So the first talk is about non-malleable codes, and the second talk is about leakage resilient secret sharing. So the first thing you may want to ask, what does non-malleable codes and leakage resilient secret sharing have anything in common? Yes, actually, to define both of them, you need to carefully specify what's the adversary model. For non-malleable codes, you need to specify what is temporary model. For leakage resilient secret sharing, you need to specify what is leakage model. And interestingly, in both areas, there are a lot of intensively works about a model called local models. And more interestingly, now there's a trend to let's move from local to more global temporary models. For example, AC0, or more general, linear low degree functions. So this section, I call them Go Global, which they try to design those primitives for global adversary models. Okay, let's go to the third collection of talks. So for the third collection of talks, I don't want to talk too much because it's very easy to spoil the talk. And so I want to just copy some comments from our discussion. So I label this collection as simple and neat. And you should explore them by yourself. Hope you enjoy the talks. Okay.
All right, thank you very much, Xiao. I guess we are ready to start the talks. The first talk is demultiplicative secret sharing for multipartite adversary structures by Reo Eriguchi and Noboru Kunihiro. And Reo will give the talk.
Oh, well, thank you for your introduction. Today, I talk about a special class of secret sharing schemes called demultiplicative secret sharing. So I explain the definition of secret sharing. We assume that there are n players, and an adversary can corrupt a subset of players, and we define an adversary structure, delta, as a collection of such subsets. And then the delta has a monotone decreasing property. And we suppose that the domain of secrets is a finite field of size q. And we let Si be the set of the ith shares. Then a secret sharing scheme is a randomized function whose input is a field element and output is a tuple of n shares. And then we call the secret sharing scheme a delta private if no information on a secret is revealed from any subset in delta. And we measure the efficiency of the secret sharing scheme by the total information ratio, which is defined by the ratio between the total size of n shares and the size of a secret. So it is important to minimize the information ratio to obtain efficient schemes. Now I provide the definition of demultiplicative secret sharing. A secret sharing scheme is called demultiplicative if there is a deterministic function mult for each player I. This function takes d shares as inputs, and if each share corresponds to the ith share of the secret Sj, then this function generates an additive sharing of the product of d secrets, S1 to Sd. And then, in other words, the players can locally compute an additive sharing of the product from their own shares. Now, demultiplicative secret sharing can be used to construct two-round and conditionally secure multi-party computation protocols for computing multivariate polynomials of total degree at most d. So I show a simple protocol for computing the product of d secrets. We suppose that each client has his secret input, Sj, and then each client shares his inputs among n servers by using demultiplicative schemes. And then each server can locally compute the function mult and obtain the additive sharing of the product. So finally, an output client collects these additive sharing and recovers the desired output. So now the communication complexity of this protocol is proportional to the information ratio and the bit length of the field size. And the protocol is passively secure against an adversary structure delta. So it is important to construct demultiplicative secret sharing such that information ratio and the field size are small, and it is delta private for a large adversary structure delta. Now, I briefly show the previously known results about demultiplicative secret sharing. First, as a negative result, delta private and demultiplicative secret sharing exists only if the adversary structure is of type QD. That is, no d subsets in delta can cover the whole set P. And on the other hand, for any adversary structure delta of type QD, it is possible to construct demultiplicative schemes for delta. But this scheme is very inefficient due to exponentially large information ratio. And if d is equal to 2, a more efficient construction based on linear schemes is known. And Shamir scheme is also demultiplicative, but this scheme can deal with only threshold adversary structures. And finally, to reduce the field size of Shamir scheme, demultiplicative schemes based on algebraic curves were devised. So if we choose an algebraic curve with many rational points, we can obtain demultiplicative schemes over smaller fields than the Shamir scheme. And now I explain our proposed secret sharing scheme. Our scheme can deal with multipartite adversary structures. So suppose that P is divided into L parts, P1 to PL, and we call a pi permutation if it maps every player in each part to the same part. Then an adversary structure is called bipartite if the image of every subset in delta by any pi permutation is also in delta. So informally, in a bipartite adversary structure, whether a subset X is in delta or not is uniquely determined by the associated vector defined like this. So now, for example, threshold adversary structures are one partite adversary structure with respect to this trivial partition. And then every adversary structure can be viewed as an n-partite adversary structure with respect to this partition. And now I show our main results. In this work, we propose two kinds of demultiplicative secret sharing for L-partite adversary structures. And the first scheme can be applied to any L-partite adversary structure of type QD. Because there are demultiplicative schemes only for QD adversary structures, so our scheme can deal with all the possible L-partite adversary structures. And this scheme has polynomial information ratio, or if L is constant. So our scheme is much more efficient than the generic construction. And more precisely, the information ratio is upper bounded by the size of this set of vectors, which consists of all the maximal vectors with respect to the coordinated order. And next, the second scheme can be applied to L-partite adversary structures satisfying this geometric condition. And this condition is a stronger assumption than type QD. So the second scheme can be applied to a smaller class of L-partite adversary structures than the first scheme. But this scheme has smaller information ratio than the first scheme if epsilon is not very small or constant, for example. And finally, I briefly remark on future work. Both of our schemes require the field size to be sufficiently large. So future work is the construction of demultiplicative secret sharing over smaller fields. This can reduce the communication complexity of the protocol. And another one is an extension of our proposed scheme to the verifiable demultiplicative schemes, which can detect the malicious behavior in the protocol. That's all. Thank you.
All right, thank you very much. So we're going to leave any questions to the end, and we're going to proceed with the second talk. The second talk is leakage resilient secret sharing in non-compartmentalized models by Lin, Charakchi, Guruswamy, Safavi Naini, and Wang. And Fuchun Lin will present this work. If you can share your slides. Okay.
Okay, can I start?
Yes, go ahead.
So a simple example of secret sharing scheme. You divide the secret into several parts, several shells. And if you have enough number of
just a
shells,
comment that there's the build order on top of your screen. Could you, there's this window, it sometimes pops up in Keynote. If you can close that window.
okay.
Yeah.
And I'll do it again.
All right.
So if you have enough number of cells, then you can recover the secret. Even with one cell less, then you have no information about the secret. And usually the privacy here is perfectly private, but also there are some times people consider statistical secret sharing, use statistical distance to measure the amount of leakage. Shamir scheme is a threshold scheme. It can be interpreted as encoding a random message using an MDS code. And then you do the vector matrix multiplication to generate shells. It's easy to see that with enough number of cells, you can reconstruct the secret. In fact, you also reconstruct the randomness and the full shell vector. This is called full reconstruction in secret sharing scheme. And you can easily see that with one cell less, then the distribution of these T-1 cells are uniform, and it is independent of which secret you are encoding. Now the question is, what if the adversary can dig beyond this standard any arbitrary T-1 cells? For example, the so-called local leakage model. You can dig a few bits, a bounded number of bits from every shell. And there's a result from coding theory that says that if you have a Reed-Solomon code, which is basically secret Shamir scheme, and then if you have a component broken, then you can download 1 bit from each component to repair that component. And in secret sharing scheme, this means that we can download 1 bit from each shell and recover the secret. This says that this secret sharing scheme is completely not leakage resilient with respect to local leakage. But on the other hand, there's a result saying that if this Shamir scheme, the underlying finite field is a large prime, then it is actually leakage resilient with respect to local leakage model. That means the adversary can apply arbitrary leakage function independently to each shell and leak a bounded number of bits. And of course, here you cannot hope to have perfect privacy or a perfect leakage resilience. You have to tolerate epsilon measured by statistical distance. So we can see that if the adversary is stronger than the standard model, then Shamir scheme itself is not enough. And later people consider even more stronger than local leakage. They consider joint leakage, and they also consider adaptive leakage, and they need more and more complicated techniques to construct the secret sharing, leakage resilient secret sharing scheme. So in this work, we look at a global leakage model. We are allowing the adversary to access all the shells at the same time. And since we are allowing the adversary to have access to all the shells, we have to restrict the leakage function that are allowed for the adversary. Otherwise, the adversary can simply use the reconstruction algorithm and reconstruct the secret and output only 1 bit. So we restrict the adversary to some structured class of leakage functions. And the adversary can choose arbitrary function from that class. The adversary can, as in the standard model, ask for several a bounded number of full selves.
What?
If the adversary commits
What?
to the queries before the game, then this adversary is called non-adaptive. We also consider adaptive adversary. For example, the adversary can first apply a global leakage function, leak some number of bits, and according to these results, he make the choice of the full selves and continue in this adaptive fashion. Okay, this is our technique. So we have just seen that Shamir scheme is not enough for fancy leakage. And what we do is we use a randomness extractor to mix up the secret and the randomness before we input into the Shamir scheme. Since we are using a randomness extractor, we first assume that the secret has a uniform distribution. And if we input the uniform secret together with the randomness into the inverter of an extractor, we get a uniform preimage. And then we interpret this uniform preimage as T finite field elements and do the Shamir scheme. Now suppose an adversary apply a leakage function and obtain the leakage conditions on this leakage, the distribution of the uniform preimage becomes non-uniform. But if your extractor can extract uniform distribution out of that distribution, then you recover the uniform secret. So in this sense, you see that the secret and the leakage are independent. And that means leakage precedent. So we use this idea and give 4 example constructions for different leakage adversaries. For example, if the adversary is an affine adversary, it can only apply degree 1 leakage function. Then we use affine extractor. If it is a degree D polynomial, then we use the corresponding algebraic extractor. And when the adversary is non-adaptive or partially adaptive, we also can use seeded extractor. Here are some more details. So the kind of extractor we require, firstly, it has to be invertible, since we are using the inverter to do the shell algorithm. For example, if the extractor function itself is a linear function, then it is efficiently invertible. In the case of linear seeded extractor, it is. And we want the extractor to be able to extract from any constant fraction of entropy. This is because we have a uniform preimage that's about the amount of T finite field elements. And we allow the adversary to leak T-1 finite field elements. So we only have 1/T fraction of entropy left if we want to have a threshold scheme. And of course, we want the extractor to be able to extract all the randomness. In that case, we will have we can extract all the amount of remaining entropy is 1 finite field element. If we can extract all the randomness, then the secret length is equal to the cell length. This is as good as the Shamir scheme. Usually, you you can only extract all the randomness using a seeded extractor. And in that case, we need to also include the seed. And then we then need the seed to be of negligible length. And finally, we want to have very small extractor error. Since the extractor error is not equal to the leakage resilient error, there is a blow up. And if we don't have small extractor error, we can get annoyed using some special structure. For example, if your extractor is linear and your leakage function is affine, basically you have an affine source, affine distribution. When you apply a linear function to an affine distribution, you get an affine distribution. And affine distribution is equal to uniform if the dimension is equal to the universe. Otherwise, it's going to be at least one dimension less than the universe. Then the statistical distance is going to be very bad. In this case, you can get a stronger result. That says that for most of the cases, you get extractor error 0, and only for a negligible fraction, you get a big extractor error. And then in that case, the extractor error becomes equal to the leakage resilient error. So putting all these nice properties together, for the long-adaptive adversary and affine leakage, we get a leakage resilient version of Shamir scheme. The secret length is equal to the cell length, and you can tolerate whatever leakage, the affine leakage, and together with the full cell leakage, as long as the total amount of information given to the adversary is at most T-1 cell in size. Okay, I will stop here.
All right, thank you very much. The next talk is on polynomial secret sharing schemes by Paskin, Chernyavsky, and Radun, and Anat will give the talk.
Good, so sharing the slides. Yeah. Just a second. Okay, seems to be working. Okay, thank you for the introduction. I'm happy to present our work here at the first ITC. And I'll talk about polynomial secret sharing schemes. So let's have a quick recap of what a secret sharing scheme is. So a secret sharing scheme allows a dealer to share a secret among some n parties according to some X structure. That is, sets of parties that are qualified according to that X structure will learn the secrets, while sets which are not qualified will learn nothing about the secret. So that setting was introduced by Shamir and Blakely in the late 70s, and for the threshold case, and generalized for general monotone X structures a few years later. And we focus on the perfect, okay, just also let me mention that general secret sharing schemes in this talk, the most general setting is one where the randomness is sampled uniformly from that finite domain R. Now we will focus on perfect secret sharing, where every authorized set recovers the secret with probability 1, while unauthorized sets see shared distributions which are independent of the secret, completely independent. Now, a very useful type of secret sharing schemes are linear secret sharing schemes, where the secret domain is some finite field, and the randomness is some vector over the same finite field of some fixed length, and the shares are comprised of multilinear polynomials in this secret and randomness elements. Now, this type of schemes is very popular. Most schemes constructed so far are linear, both because it has nice structures that are useful for many applications like MPC, and also its relative simplicity is kind of conceptually nice for designing schemes. And let me mention that schemes with polynomial share complexity only correspond to X structures which are in NC. So what is share complexity? So recall the share complexity is arguably the most important complexity measure of secret sharing schemes, is simply the total length of shares obtained by all parties in bits in the worst case. And sometimes we're only also interested in the information rate, which is the share complexity normalized by the secret length. And we have a huge gap between the best constructions for the worst X structures known, which are exponential, and the best known lower bounds, which are not even quadratic. And the latter is in spite of some quite exciting recent advances on the upper bound front. Now, note that this lower bound hasn't changed for over 25 years. On the other hand, for linear, as Yao mentioned in the intro, schemes were doing much better. So the upper bound is best known is still exponential, but the lower bounds are also exponential. So there is still some gap, but it's much, much better. Also, let me mention that for a fixed constant field size, it is easy to obtain exponential lower bounds just by counting for certain X structures, while the more recent results, including this recent preprint, are stronger in the sense that they apply to all fields. On the other hand, for general schemes, even counting-based approaches don't work. So we don't have any better existential results even. Okay, and the multilinear scheme generalizes linear schemes, allowing the secret to also be a vector rather than a single field element. So these schemes have also been studied somewhat broadly, but somewhat less, and their advantage is that they may help us improve the information rate. And indeed, there is some recent evidence that this is possible. And here, on the lower bound front, we are doing much better than in the general setting, but still worse than for linear schemes. So in this work, we introduce a natural generalization of multilinear schemes to which we call polynomial secret sharing schemes, where we simply allow the polynomials appearing in the various shares to have any degree, not just degree 1. And our main motivation is that the hope that we can obtain better than general lower bounds for this broader class generalizing multilinear. And it's a good starting point is considering degree 2 polynomials. And in the long run, hopefully, this could help us make inroads into into lower bounds on general secret sharing schemes, especially as polynomial schemes are very expressive and essentially, at least in the statistical setting, they're as general as you can get, basically. So let me quickly mention some results. So on the share complexity front, we have some negative results. The first result saying that degree 1 in R, almost all of these schemes, some large subset of such schemes, are actually as powerful as multilinear schemes, in the sense that any such scheme has an equivalent multilinear scheme with almost the same share complexity, maybe with some overhead n, and over the same field. And for degree 2, we show that linear terms in R must be present, or else, even regardless of share complexity, one can only implement some very simple X structures. Another aspect to consider is the randomness complexity. So let me try to convince you that it is important. So for multilinear schemes, without loss of generality, the randomness complexity is upper bounded by share complexity. That is, you can reduce the randomness complexity that much without losing on share complexity. For degree 2, for instance, nothing like that is known. And if we had such a bound, even a much worse bound than this one, this would imply a counting-based lower bound on share complexity, which is already better than for general schemes. And there are also additional nice applications that for upper bounding the randomness complexity that I will not mention here. So we have made some progress on this front. So for quadratic schemes, we've shown that any such scheme has an equivalent scheme with the same share complexity and randomness complexity, which is exponential in the share complexity. The exponent is not very horrible here, but still it's not good enough for implying good lower bounds on share complexity. And for general schemes, we also obtain a similar bound. And let me mention that our proof also implies a similar bound for completely general perfect secret sharing schemes. And while such a bound is quite trivial for statistical bound schemes, we can even get a better bound. But as far as we know, it was not known for perfect. I didn't find any, so correct me if I'm wrong. And finally, let me just mention that there is a lot of future work and interesting open questions like the randomness complexity, for instance, and many more. And you're welcome to take a look at the longer slides or the paper. Thank you for your attention.
All right, thank you very much for the talk. If there are any questions during the talk, you can just post on Q&A or the chat, and in the end of the session, we go over them and ask the speakers. So let's proceed with the fourth talk, which is on locally decodable codes in resource-bounded channels by Jeremiah Blocky, Shubhang Kulkarni, and Samsung Zhu. And Shubhang will present the work.
I think the screen has to be stopped sharing.
Yeah,
I didn't stop. Okay, sorry.
All right, cool.
Yeah.
Okay. So thank you for the introduction, and hope everyone enjoys the talk. So our story begins with the need for reliable communication. Let's take a look at this Mars mission, whose goal is to confirm the presence of water. Knowing that space is noisy, we should add some sort of redundancy to our message so that when space corrupts the transmission, Earth can recover it as intended, in this case, by a simple majority vote. You may notice, however, that reading the entire transmission and recovering the entire message is quite unnecessary for Earth in this case. In particular, it suffices for Earth to just recover the first Y symbol, and it can do so by making just 3 local queries to the transmission and taking a majority vote. So this is the setting that we'll be interested in. And let's abstract away the details and establish a simple model. So sender and receiver are communicating over a noisy channel. To combat the noise, the communicating parties encode and decode the message. We're interested in the setting where the receiver wants to decode a specific, say the ith symbol of the initial message. And for this, the decoder gets query or oracle access to the corrupted code word. Now, the goal of the communicating parties is to design codes for reliable communication, which we take to be recovering the ith bit with, say, good probability. At the same time, we hope to minimize the communication cost, which for us just means low code word length and a small number of decoder queries to the code word. And finally, we also want to maximize the communication robustness, which we're going to take to be tolerating a large number of errors from the noisy channel. So let's take a look at the channel. And actually, modeling the noisy channel is crucial for the design of good codes. And historically, they've been modeled as 2 broad categories: Shannon channels and Hamming channels. So Shannon channels are purely probabilistic and flip each bit of the code word independently at random. On the other hand, Hamming channels are adversarial and introduce worst case error patterns into the code word, subject to some upper bounds on the number of errors. Both of these have their pros and cons. So Shannon channels admit good LDCs with very good properties, but these error patterns don't capture scenarios such as, say, burst errors in nature very well. On the other hand, since Hamming channels are worst case, constructions for Hamming channels have broad application. However, there are no known good LDCs with good parameter trade-offs in Hamming channels. So for the purposes of this talk, good properties is going to mean constant rate, polylog locality, and constant error rate. So you may observe that these models seem to be opposite extremes, and our work begins by asking the question of what are practically motivated channels admitting good LDCs? So let's go back to our Mars example. While sending messages back to Earth, our spacecraft is actually beaming the transmission using electromagnetic waves. And so a few practical observations are that the maximum Earth-Mars distance, as well as the speed of light, are upper bounded. And we can immediately conclude using these bounds that space has a bounded amount of time within which it has to corrupt the message. In fact, we can calculate this bound to be approximately 22 minutes by plugging in our observations. And so the point is that space isn't an unbounded adversary, and so assuming so is overly pessimistic, which leaves us with the natural question of whether including this time bound in our channel model would be beneficial for LDC constructions. And our work answers this question with a yes, but in the parallelogram oracle model. This is an idealized setting where cryptographic hash functions such as SHA-3 is modeled as a purely black box function. Of course, we aren't limited to just time bounds, and we can consider any resource bounds. So how do we do this? Our first technical tool will be private LDCs. So these are LDCs defined in the setting where the communicating parties have shared secret keys, so the channel does not know these keys. Ostrovsky, Pandey, and Sahai showed constructions of private LDCs with good properties under our notion of goodness. Note that in our setting, the communicating parties don't possess shared keys. So if we were to use these constructions, the encoder would need to find a way to securely signal a key to the local decoder. Our second and final tool will be that of a safe function, and we're going to use safe functions to solve our previous problem. Intuitively, a function is safe against a channel if the channel cannot predict the value of the function given the input. In slightly more formal terms, it can predict the value of the function with probability at most delta. So a few intuitive examples are that hash iteration is safe against sequential time-bounded channels. And memory hard functions such as scrypt are safe against space time-bounded channels. In our main paper, we formalize various resources and discuss various safe function constructions for these resources. And I refer you to the main paper for this. So let's put everything together and take a look at the LDC framework that bootstraps private LDCs. So given an input message, the encoder first randomly samples a small seed and extracts a secret key using the safe function of the channel. This is done in the parallel random oracle model. The extracted key can then be used in conjunction with the private LDC encoder to encode the message. Finally, an encoding of the seed is appended to the message encoding, and the entire encoding is sent over the channel. The local decoder is going to get query access to the corrupted version of this encoding, along with the index to decode, which is shown in red. It first decodes the seed and extracts the same key via the safe function. Finally, it uses the private LDC decoder to get the original intended symbol. Of course, this is a very high-level overview of the framework, and I would encourage you to look at the main paper for details. So recall the private LDC constructions of Ostrovsky et al. Had our target good properties. And in our main paper, we show how to encode the seed so that it can be locally decoded. And our final framework is able to inherit the good properties from the private LDCs with small loss. In particular, we get polylog locality, constant rate, constant error rate, and high probability of decoding. And so in conclusion, resource-bounded channels better capture realistic error patterns that occur in nature, and we can actually construct efficient LDCs for these types of channels. We can do so by using safe functions to extract private shared keys between the communicating parties. And these can be used to bootstrap off of private LDC constructions. Our work leads to a few interesting open questions of what are other applications of these safe functions that we've defined, and also whether there are LDCs for resource-bounded channels without random oracles. Thank you.
All right, thank you very much. The last talk of the session is Expander Graphs on Non-Malleable Codes by Rasmussen and Sahai, and Peter will give the talk.
Yep. All right. Wait, is my screen shared yet? Okay.
Not
wait.
yet.
No.
Why is it not shared? Oh, right. Okay, wait, now I got it. Let's see. Okay, like this. How's that?
Perfect.
Okay, great. Let me just like this. All right. Hi everyone. I'm Peter, as mentioned, this is joint work with Amit Sahai. Title of the paper is Expander Graphs are Non-Malleable Codes, and we're lucky enough that this is in fact also basically the main theorem of the paper. So right, the main theorem, let's jump right into it. It says that if you have a d-regular graph on n vertices and you have sufficiently many vertices, and this is a sufficiently good expander graph, then you have a good non-malleable code for single bit messages in the split state model. And okay, so we'll start off by unpacking what a non-malleable code is, and what the split state model is, and then I hope you'll understand what this means. Right. So first, codes, as we just have described, we want to send some message across a channel controlled by an adversary. And to do so, we take the message, we encode it, and then we allow the adversary to apply some tampering function f to the encoded message, and then we hope that the message survives in some way. So in this model, we have, at least the one I'll describe, we have two dials. We have basically, we can ask, what do we mean that we preserve integrity of this message? And the other is, what functions do we allow the adversary to apply? And this is an information theoretical questions. The encoding and decoding functions are publicly available and such. Anyway, let's move on. So just to give an example of this, for error correcting codes, typically the class of functions f that the adversary can choose from can only change, any function from that can only change some fraction of the bits of the encoded message. And in this case, we get a lot of nice stuff. We get great rates. We actually are just simply able to preserve the entire message. But suppose we had a stronger adversary that, for instance, were allowed to switch out the entire code word, then we can't hope for as much. So this is what Zembowski, Pietzak, and Wicks set out to investigate in 2010, and they defined non-malleable codes. So non-malleability is trying to capture these stronger adversaries, and with non-malleability, what we're trying is that there should be no meaningful tampering of the message from start to finish. And to define meaningful tampering, let's instead define what do we consider trivial tampering. So if the adversary simply copies the message, we consider that pretty trivial. If they change it to some constant message unrelated to the starting message, or if they change it to some nonsensical message that's just, yeah, they just scramble the message, then we just also consider that trivial. So for instance, you can't say, if we had encoded an integer, you can't say m+1, like this we shouldn't allow. And essentially the model is that it's a non-malleable code if with very low probability, the adversary can do anything beyond this. Right. So this is a very short talk, so this will be the description we'll use. Right, so for the split state model, so this is what functions the adversary are allowed to apply. So the model is the following. You encode a message M by encoding it into two separate code words. And then you allow the adversary to apply any function to the left code word and any function to the right code word. And then you decode. And so this is the model that you want to defend against. And this took a while to do anything about. So this was defined in 2010, as I mentioned, and then it took until 2013 for Zembowski, Kasana, and Obrimsky to come up with a construction for just a 1-bit non-malleable code in this split state setting. And after that, a lot of great work was done inspired by this. And almost all of it based on this idea of using two-source extractors. And this has led to some excellent non-malleable codes. You can get really good rates. You can encode messages of any length. And so this is not what we improve in the paper at hand. We're going in an opposite direction. We're trying, could we construct non-malleable codes from something else? And then our result is that you can actually just use expanders instead of two-source extractors. And that this gives a much simpler proof than the existing ones, or at least more elementary. And now I guess the obvious thing to consider is, well, two-source extractors and expanders are related in some way. But first of all, expanders have been around for a really long time. They're very simple to define. Most two-source extractors are expanders, but maybe not so much the other way around. And so the idea is that, well, or our result is that something as simple as expanders actually lead to non-malleable codes. Right. And so now, an obvious question is, how do you actually get a code from a graph? And the construction is inspired by the original paper by Zembowski et al. You take your graph and then you encode a message as a bit as two vertices of the graph. And then you say that you've encoded a 1 if there's an edge between the two vertices and a 0 otherwise. And you simply encode by just uniformly sampling given this. And then if this is your code, if this is the code you get from a graph, then the result is that if you have a sufficiently large graph with sufficiently good expansion, then this is a 1-bit non-malleable code in the split state model for single-bit messages. Right. So what could we hope to do with this? Well, first of all, it's, at least I think, so interesting in its own right. But then the idea or the hope would be that we could further, just like the Zembowski et al. Paper started basically non-malleable codes on two-source extractors, that we could do something similar with expanders. To do that, we would need to be able to encode longer messages, add leakage, for instance. And the hope would then be that we would be able to get simpler non-malleable codes with more elementary proofs, and with more elementary methods. And perhaps that this would lead to some deeper understanding of non-malleable codes. Right. Thanks for listening in.
All right. Thank you very much. So this concludes the 5 talks of the session. Now we have a lot of time for questions, and already we have a few on the chat. So let's start with the ones for Peter, because he's already talking. So I see that there's a question: is there evidence that there is no hidden extractor structure in the graph approach? So just to add to that, is there a connection between extractors, two-source extractors and expanders that might be exploited to extend your results to or provide connections with the extractor-based approach?
Right. So first of all, I should mention that I'm in no way an expert on extractors, but it's my impression that there is. How can I say this? Sorry, I'm just rereading the question. I'm not sure whether there is some hidden extractor structure, and I'm not aware of any extractor constructions directly from expanders, but I might be wrong. I guess the one way to look at this problem, just preempting another question that I can see here on the screen, is that you can just view one of these 1-bit non-malleable codes as a graph, right? Like you can see all possible, at least if the left and the right messages have the same codomain or same range, then you can just put an edge between all pairs that encode a 1, right? And then you get a graph, and the question is then how do you make up a graph that is a non-malleable code? And one way to do this is, as Zembowski et al. Did it, to use a two-source extractor to construct this graph. Another way is just to ask, so what is what property of the graph would be sufficient? And here it turns out that that expansion is sufficient.
Thank you. There's a related question in Q&A by Joao, who asks, which properties do you need from your graph to get explicit non-malleable codes? So I guess what's the necessary requirement that you're using?
So in the, I'm not entirely sure what that means, but in the proof, we just use that the graph satisfies the expander mixing lemma. And since this is equivalent with the spectral expansion, I think like any graph satisfying mixing lemma also is an expander. So I think basically that is all. Right.
I see. Another one is, do you also need randomization for the construction of non-malleable codes from expander graphs?
No, you can use explicit constructions. So details are in the paper, but there are some very nice constructions of expander graphs that you can just plug and play with. And also one thing here is that you you're not required to have very low degree, which is usually what you want in expander graphs. Actually, you want to have high degree. And with high degree, it's very easy to construct very good expanders.
Okay, great. In the chat window, I see, in general, can we consider K coloring the complete graph and use that to encode K messages rather than 2 messages?
Yes, this is an excellent question, and one that I've been thinking about for quite a while. This is one approach that could possibly yield constructions for longer messages. And again, you can just view the entire question as exactly this, right? Like if you have a non-malleable code, you could just color the edges accordingly, and then you just ask, like, what does this graph need to satisfy? But I don't know what this graph needs to satisfy. So maybe we'll find out someday.
Okay, great. So there are more questions about other talks. I think for the fourth talk by Shubhang, there's a question by Adam. Why do you need the seed to be locally decodable? Is F based on only a subset of constructions? Also, what specific classes of channels do the constructions work for? I see already Shubhang gave an answer, so maybe you could expand on that, and so that we can all hear.
Yeah, sure. So the seed has to be locally decodable in the sense it's locally decodable with respect to the entire code word. So the seed is actually used to extract the secret key. And so the seed length has to be large enough because the security of our entire protocol is going to be based on the seed length. But since the entire seed has to be decoded, we're going to have to encode it with a error correcting code. And specifically, so we can instantiate it by encoding it with, say, like a repetition code concatenated with a justice encode. But so since the entire seed has to be decoded, we also have the goal of minimizing locality. So the seed length also has to be chosen sufficiently small enough to maintain locality. And so considering all these trade-offs is what I meant by the seed to be locally decodable. So as to maintain the overall locality of polylog, as I mentioned as the parameters that we get. Specific classes of channels that we consider.
On the question.
Yeah.
Sorry. Just to follow up on that. So does the fact that your seed ends up having to be really short, and thus the pre-image to the seed has to be the pre-image to F has to be short, right, for it to be decodable without expanding the errors too much. And so how does that connect with, like, can't the channel just corrupt those positions and ensure that the seed is not properly received?
Right, but you can also, that's where the error correcting code kicks in. So for example, if you repeat the seed a bunch of times, even though it's small, and then say sample a few of those seeds and take a majority vote.
I see, so its encoding doesn't have to occupy a negligible fraction of the.
Yeah, so in our case, it actually captures a half of the entire code word, but you can.
I see. So that limits
probably optimize that. Yeah.
Rate you could tolerate.
Correct.
So you're not getting close to like existing bounds for.
So we have some. So obviously we're going to inherit the rate from the private LDCs, and we have some small loss from that because of our seed encoding.
I see. Okay, got it.
Our factor 2 loss. Yeah.
Shubhang, I'm wondering what are the known locally decodable codes for the Shannon model that don't work for Hamming?
So if you look at the Ostrovsky et al. Construction and just take away the private keys, then what you're left with you'd get as locally decodable code for the Shannon channel. Because what the private keys do is it basically makes the adversarial channel behave as a Shannon channel. So they bootstrap off of Shannon channel codes. So you can just like block your code into small blocks and encode each block using some constant rate code. And that would be And then whenever you want to decode a specific index, you just decode that particular block having small length.
I see. Does it matter what the underlying code is that you use as a building block, or could it be any good code?
So we inherit that from private LDCs, and for them, they can use any constant rate code. So that should be fine.
Another question I wanted to ask is the safe functions that you use, do you provide new constructions for various models, or do you use the memory hard functions and so on for specific models that were known before?
Yeah, we provide a few graph labeling functions, so essentially we define this notion of safe functions, and then we show how to instantiate them for specific resource bounds. But the framework works for any channel that has a safe function. But yeah, we do give some constructions, if that was your question.
So if I have my favorite channel and a safe function for that, I can plug in your construction.
Yeah, correct. But note that this is in the random oracle model, and open question is whether this can be done without random oracles.
Okay. I think another question on chat is related to, is for Anat. That says, it's my Maji, what is the simplest access structure measured by their complexity class that witnesses an exponential gap in the positive and negative result? So I guess what it means is what kind of access structures whether the lower bounds that we know, what is the gap for them with their corresponding upper bounds, if I understand it right. Could you unmute yourself?
Right. Yeah. So if I understand the question correctly, then for general schemes, the upper bounds are basically generic constructions that just work for all access structures. So right, there are no like particular witnesses which we know we do worst, as far as I know. Now for the lower bound, again, for the general one, there is a particular construction of the of some scheme. We can like Xirmaz proved that that we can do that bad. And actually, what in the context of our work, maybe let me add that Xirmaz's approach is based on information theory. Kind of entropy considerations, etc., and hopefully with our approach, like taking advantage of the more algebraic structure, let's say of degree 2 polynomials or whatever, we can somewhat improve this lower bound and give an example of another access structure, which is say a particular one which requires somewhat higher complexity, right? So share complexity. That is provable. And also in terms of counting, if we can have a good upper bound on the randomness complexity, then we can have actually a non-specific example, like we can have an existential bound saying there exists some scheme that doesn't have say the good degree to some access structure that doesn't have a good degree to scheme.
Okay, so with the counting argument for the linear schemes, if you, so I guess it easily gives 2 to the omega of n, but what is the constant behind? Is it 2 to the n over 2 or?
So if I remember correctly, like it's easy to compute. I think it's 2 to the n over 2. Like it's quite easy to do the calculation, but that's for fixed like constant fields. And the stronger bounds are for any fields from other works which are not like simple counting based. And for say degree 2, we don't have that because we don't have any like good enough upper bounds on the randomness complexity. So it could be huge, and then small, like in this randomness, is still possibly too large to be non-trivial.
Is there a consensus whether 2 to the n over 2 might be the right bound for general access structures?
So I'm not sure. I've seen recent work on right? Maybe Amos can answer. Can give a better answer, because I was going to mention one of his recent works.
Okay.
For linear schemes, the span sequence as an access, the low bound is 2 to the n over 2. The upper bound is 2 to the 0.76 n. I would conjecture, and I have famous conjectures that might not be true, that n over 2 is the right thing for linear schemes.
Okay, yeah. I see Vinod is smiling. But
I have no.
Okay, yeah, great.
I have no evidence why this is true for other classes of secret sharing scheme. What we get from the simple counting arguments turn out that the lower bounds are tight, and we find the lower bounds count for counting is simple, and we get the upper bounds. But I would conjecture that 2 to the n over 2 plus O of little o of 1 is a tight one, but and it should and it might be possible to obtain it not with more complicated tools than we have now.
And can it be obtained by linear schemes, you think?
I would say that by linear schemes. For linear, I have no way. I don't know what share size is.
Okay, so we have that recorded now. Another question, I think it's for Shubhang. Is there a connection between safe functions and one-way functions?
So the definitions are quite similar, but I haven't explored the connections per se. So I can definitely talk about it offline if anyone's interested.
Okay, it seems like we have more votes for 2 to the n over 2. Very popular bound. Another question I see is from Adam. If you have time and don't have questions for Shubhang, is there a connection to recent work by Shaltiel and co-authors on regular error correcting codes for space-bounded channels? They hide the locations that encode the seed, which means that they do not lose rate relative to the secret key construction. Shubhang already says I'm unfamiliar.
Yeah, so I'm kind of unfamiliar with that work, but definitely looking it up right now. So
okay, yeah.
I'd love to talk to Adam offline.
Yeah, that definitely seems relevant. Okay. It seems like the time is up and we have to take the break. Thanks everyone for the great session. We can continue the voting on 2 to the number 2 offline. And yeah, see you after.
Okay, so we resume at 10:30 Eastern Daylight Time.
Adam, can I try projecting my slides?
Yeah, go ahead and try it out.
Mhm. Yeah, that should be it. Okay.
Yeah, that looks good.
That's good. Okay, all right, I'm going to stop sharing.
Hey, Vinod, so we'll be starting in about a minute. Do you want to try sharing your screen?
Yeah, sure. Let me try.
Maybe, okay.
Let me try. Yep, should be visible, right?
Yep.
And can you hear me well?
Yes, perfect.
Good, excellent. So Zoom kicked me out in the middle. I think we'll see in the should be yeah.
Amos, are you there to do the introduction?
Yes, but I cannot start the video. The host stopped it.
Oh.
Okay. So should I start or wait another minute?
Let's start.
Okay, I'm happy to introduce Vinod Vaidyanathan. I apologize for my pronunciation. Vinod is a professor at MIT. He's known for his major contribution for lattice-based cryptography, building fully homomorphic encryption and other primitives. He won numerous awards. He won the Joseph Raviv Fellowship from IBM, a Sloan Faculty Fellowship, Microsoft Faculty Fellowship, NSF Career Award, DARPA Young Faculty Award, Howdy Edgerton Faculty Award, many awards. He's a great researcher. Secret sharing schemes was not his main subject of research, although one of his first papers was on computational secret sharing scheme. While he was still doing his undergrad studies in India. In a series of results with his co-authors, Ren Liu and Hotek Wee, they gave a surprising upper bound for secret sharing schemes. Previously, for nearly 30 years, the upper bound was 2 to the n, and they showed that the upper bound is 2 to the c2 at the end, where the c is smaller than 1. Very surprising and a breakthrough result. And we're not telling us about that.
Okay, thanks, Amos. And thanks, Daniel and the PC for inviting me to speak. It's a real honor. I just want to sort of say, can everyone hear me well, loud and clear? Yes.
Perfect.
Yes.
Okay, beautiful. All right. So so as Amos said, this is not my main research focus. But this is a problem that I started sort of thinking about from the time I was a sophomore. Like completely clueless sophomore. And one of the first papers I read was Amos and Yuval's paper from 2001 on nonlinear secret sharing, and that really was what sort of captured my imagination. Of course, I couldn't solve any of these problems, and it actually took Tianren and Hotek to do the hard work and solve the things. So I'm happy to sort of talk about this series of works. It is actually a series of 3 papers that appear in Crypto, Eurocrypt, and Stock in the last 2 years. Okay, so let's get started. Okay, so we've heard about secret sharing quite a bit from the last session, but nevertheless, let me sort of define it. Let me set the stage. Secret sharing is a wonderful primitive in information theoretic cryptography where you have a dealer who has a secret B, and you should think about B as a bit throughout this this talk. And what the dealer wants to do is he wants to run a randomized procedure on the bit B and create a set of n shares that each share you give to one party. There are n parties. And what you want is that any authorized subset of parties can get together, pool their shares together. They can recover the bit B, but that's it. No not authorized subset of parties has any information about the bit B. Okay, and in fact, this definition of which sets are authorized and which aren't is part of the sort of the definition of the secret sharing scheme. If you must have heard about secret sharing scheme if you are in this community in one form or the other. In fact, secret sharing was defined by Adi Shamir and Bob Blakely, back in the 70s. And the way they defined it is for what are now called threshold access structures. Namely, the definition of access structure is that any set of size more than or equal to T can reconstruct, and only those sets can. So that's called a threshold secret sharing scheme. A few years later, Ito, Saito, and Ishizeki generalized this to sort of general secret sharing schemes, where the access structure can be an arbitrary collection of subsets of parties, except if you peer carefully at the definition, you realize that if a set of parties can recover the secret, so can a superset of the parties. Right? They have strictly more information. So you can't have an arbitrary collection of subsets. You have to have a monotone collection of subsets. But of course, that's the only restriction. You can define an access structure to be an arbitrary monotone collection of subsets. Okay, and that's the sort of the focus of today's talk. In fact, again, just to set the stage and to lay some ground rules and notation, I'm going to talk about subsets of parties. I'm going to sort of, that's the same as sort of an n-bit string for me, right? So the string is the characteristic vector of the subset. A collection of subsets of n parties is a Boolean function on n bits, right? So it's a function that says, given a subset, is it in the access structure or not? That's the Boolean function. Like we discussed before, not all Boolean functions are permissible. Only monotone access structures, or in other words, monotone Boolean functions are valid access structures. Okay, so this is just sort of notation, just lay the terminology. And I'm really, in fact, going to go back and forth between sets and functions, and I really think about them as the same. All right, so like I said before, this talk is about general secret sharing scheme, in other words, secret sharing for arbitrary monotone access structures. And really the key measure of interest in the literature and among people, and for today certainly, is the communication complexity of a secret sharing scheme, which is the total size of all the shares that the dealer sends to all the parties. Okay, so this really is the communication complexity problem. So what do we know about general secret sharing schemes? Back in the 80s, Benello and Leiter showed a way to take a monotone Boolean formula that computes the access structure, computes the access function, and turn it into a secret sharing scheme for that access structure. And the feature is that the size of the shares in the secret sharing scheme was proportional to the size of the formula, the size of the monotone formula computing the access structure. Okay. Shannon told us that, in the worst case, you need size 2 to the n formulas, even circuits actually, to compute a worst case access structure. In fact, true also for monotone functions. And therefore, in the worst case, Benello and Leiter will send 2 to the n bits for the worst possible access structure. Right. Karchmer and Wigderson a few years later sort of came up with a different construction, starting from what's called a span program, or rather a monotone span program. And again, they proved a very similar result. For monotone span programs, the best known construction for the worst access function, again, has size 2 to the n, no better than formulas. The counting lower bound, as we discussed, as Anat mentioned at the end of last session, is 2 to the n over 2. Okay, so there's a little bit of gap, but really both are exponential. So you see a theme in these two results, right? So the way people constructed secret sharing schemes for the large parts was to start from a computational model for the access structure or access function, so be it formulas or span programs, and turn it into a secret sharing scheme where the communication complexity, the share size, depends on the size of the computational model, the size of the formula, the size of the span program. Okay, that's the way things work. And really you have to wonder why it must be the case that a purely communication measure has to depend on the computational cost, right? I mean, it makes, if you haven't thought about this at all, if I just tell you this problem, it just sounds bizarre to you, right? I mean, surely one must be able to do better, right? So again, sort of, to tell you what the state of the art is, here's the graph. The y-axis is a share size. In fact, I'll write it in logarithmic. It's a logarithmic scaling, right? And I'll scale it down by n. So log of the share size divided by n is the y-axis, and that's can't be smaller than 0. And we know that there is a 2 to the n size scheme, so that's 1. So log s over n is 1. Okay, so that's what we know at this point. What is the lower bound? Do we know lower bounds on this stuff? And again, sort of as some of the previous talks mentioned, Shermas in the 90s proved that you can't do better than n squared over log n for the total share size. And in the logarithmic scale, that is 0. Okay, so the 2 to the n versus n squared over log n. In fact, I'd like to emphasize that we don't even know a better lower bound existentially for secret sharing. That's very different from computational complexity, where all kinds of sort of lower bounds are non-existentially, and what people spend a great deal of time on is to prove explicit, sort of lower bounds for explicit sort of functions, etc., etc. Even that is so we should be even more embarrassed than the CCC people, because we don't even know better existential lower bounds. Okay. And that's for sort of the left side is for unrestricted secret sharing. Yeah, so this is what we have been talking about so far. On the other hand, if you restrict the secret sharing in a way that the share function, let's say, is a linear function, and so is the reconstruct function, it turns out. So the share function takes a bit and randomness as input, right? And you want it to be a linear function on these guys. Then again, I mean, you can't do any better in terms of upper bounds, right? It's still 2 to the n. But for lower bounds, we know that you can't do better than 2 to the n over 2. And that's because of the tight relation between monotone span programs and linear secret sharing schemes due to Karchmer and Wigderson. And sort of the counting lower bound on monotone span programs translates to a share size lower bound on linear secret sharing schemes. So that's how the 2 to the n over 2 comes in. So, the gap is somewhat less embarrassing, but there's still the gap, right? So that's that. So the question really is, can you do better? Like, which answer is correct? Is the low? Can I improve the lower bound, the upper bound? What is the right answer, right? So what we show in the work with Tianren Liu and Hotek Wei, a series of 3 works, as I mentioned before, is that every monotone access structure on n parties. So this is what we have been talking about before. For every monotone access structure, there is a secret sharing scheme with share size less than 2 to the n bits. Okay, so so we break this sort of 2 to the n thing that we've been stuck on for many years. And concretely, if you want to sort of peer into it, it's the share size is 2 to the 0.994 n bits. Okay, so maybe I should really have called my talk not breaking the secret sharing barrier, but rather a crack in the secret sharing barrier. But as we know, all cracks have a tendency to widen and widen and widen, and eventually break things. So it's sort of looking ahead down the line. All right, so that's the sort of the main theorem that I'll talk about today. We have several other results that came out of this series of works. Let me mention a few. If you want linear secret sharing schemes, the same series of works also gives you a linear secret sharing scheme, but the share size is 2 to the 0.999 n bits. Okay, so in theory, when you say 0.99 n, that's a proxy for 0.999, which is 1, but that's not the case. It really is 0.999, 3 nines, stops there, and that's that. Okay, yeah, just to be clear, we are on the same page. All right, so that's the linear secret sharing scheme. Of course, it does a little bit worse, but still it breaks the 2 to the n barrier. And finally, we show that so both of these results are for worst case access structures. For every access structure, we do this and that. What we also show is that there is a class of access structures, pretty large class of access structures. And they require circuits or formulas or monotone span programs, etc., of size 2 to the n over 2, size 2 to the omega n. But they have a secret sharing scheme which shares size 2 to the square root n bits. So this really is conclusively breaking the representation size barrier. Right? You can't have a representation of size 2 to the square root n for this class of access structure, and yet you have a secret sharing scheme of that size. Okay, and these are sort of individual results, but all this emerges out of a general framework that connects private information retrieval, which I'll define down the line, conditional disclosure of secrets, also I'll define it down the line, and secret sharing. So this is sort of a very interesting sort of connection between all these things, and that's sort of what we exploit. In fact, there are sort of other results down the line. They use these connections, they improve these connections with very interesting ideas, and they have sort of made our results better. In particular, the sequence of works, the latest being work of Applebaum, Amos, Baimal, Oded Nir, and Nati Peter. It's going to appear in stock, so you should go to the talk next week, sort of an advertisement. And they improve our 0.994 to 0.637. Okay, sounds you should be a little bit better. You should feel a little bit better with 0.637 than 0.994. Okay, and similar improvements for linear secret sharing schemes. It's what Amos mentioned during the break. It's 2 to the 0.762n secret sharing. So these works use the framework, but they extend the framework in very, very interesting ways. And finally, there's a recent preprint of Amos and Farash, I forget his first name, who show that most access structures, really like most access, it's not like a class of things, but most access structures have a secret sharing scheme with share size 2 to the square root n bits. So that again sort of vastly improves our third theorem. Okay, so that's sort of the state of the art at this point. And really, what I want to tell you about is the very first theorem, and we'll see how far we get with that. But I want to sort of at least tell you the interesting ideas that go into it. Okay, so we do this in 3 steps. Those are the 3 papers, really. And the first step is we start from this primitive called conditional disclosure of secrets, which I'll define in the very next slide, or maybe in 2 slides. And that we show, we sort of observe a connection between conditional disclosure of secrets and sort of secret sharing for a certain class of access structures called graph access structures, or forbidden graph access structures. This was known before, sort of well known within the community. And what we show is a new CDS protocol with communication complexity 2 to the square root n, and that sort of gives you a new sort of secret sharing scheme for these graph access structures. So it's not all access structures, it's a class of things, but it's a new thing. The second work sort of generalized this not to graphs, but to hypergraphs. And again, we don't lose in the communication complexity at all. We show sort of instead of a 2-party CDS, which I'll define again in a little bit, we show an n-party CDS. We don't lose anything in the communication, more or less. It's 2 to the root n stuff. And the new technique the new technique in the CDS construction is the connection to private information retrieval. The new technique here is something called matching vector families. Again, I'll tell you much more about it down the line. And the final work actually lifts all this into not secret sharing for classes of access structure, but really secret sharing for all access structures. And that's where we hit the 2 to the 0.994. And you really should be in suspense at this point. Like, why? What is this 0.994 coming from? I'll reveal it towards the end, I promise. And there again, there is a sort of a new technique which has nothing to do with secret sharing. It's really sort of like a circuit construction technique, and that's what we do. Okay, so these are the 3 steps, and really I want to sort of focus on the first step. That's what I'll talk for the most of the time, I'll talk about it, and we'll see sort of how far I get with the other two. Okay, so I kept talking about conditional disclosure of secrets, CDS, again and again and again. So what is this? What is this object? Okay. So here is what CDS is. It's a very, very nice communication game that was defined by Gertner, Ishai, Kushilevitz, and Malkin back in the last century, right? And what it is the following. It's a game between 3 players. There's Alice on the left, my left, Bob on the right, and there's a Charlie. Alice knows an input X in some interval capital N, right? Should really think about it as a little n bit string. So 2 to the little n is capital N for me, okay? And Bob knows an input Y also in the same sort of interval, and both of them know a bit B, single bit B. Their goal is to send a single message to Charlie, who knows both X and Y. So the only thing he doesn't know is the bit B. And they want to make sure that Charlie gets this bit B if and only if some function f of x comma y equals 1. So f is a publicly known function or a predicate. And if f of xy happens to be 1, Charlie should get the bit B, should be able to recover the bit B from the 2 messages NA and MB. And if f of xy is 0, he should get no information about B at all from these 2 messages. So that's what they want. And to help Alice and Bob out, they share a random string R in the, not quite in the sky. They both know R, but Charlie doesn't know it. Okay, so that's like the secret sort of random, the secret common randomness, right? So if you think about it, this is actually quite not trivial. So Alice would like to sort of sometimes send the bit B to Bob, sometimes send the bit B to Charlie, sometimes not, but she doesn't know when Charlie should get this bit. That depends on Y that she doesn't know, only Bob knows. In fact, she is not allowed to talk to Bob. So how in the world is this supposed to happen? Right? So that's a non-triviality. So, okay, so this sounds like a game. If you sort of peer into it, you see similarities with secret sharing, right? Somebody should get the bit sometimes, but not other times, yada, yada, yada. But but what does this have to do with secret sharing? What's the actual connection? So here's the sort of hint of the connection, and so we'll build on it later in the talk. So I claim that if you have a CDS scheme for a function f, or really let's say for all functions f, then there is a secret sharing scheme for a family of access structures called graph access structures. Okay, so what is a graph access structure? In a graph access structure, rather graph secret sharing scheme, there are 2 times n parties, right? So the purple parties on the left and the green parties on the right, there are 2 times capital N. And remember, capital N was actually the domain size of Alice and the domain size of Bob, right? So that's the capital N. And these are the parties. So now I have to define what is the access structure. When can the parties reconstruct the secret? So it turns out that no single party should be able to reconstruct the secret. So that's out of the way. Let's get that out of the way. Any set of 3 parties should be able to reconstruct the secret. Any set of 3 parties should, no one can. So the interesting stuff happens in this between sets of 2 parties, right? So now given a sort of a party X and a party Y, when should they be able to reconstruct the secret? Well, if and only if there is actually an edge in this graph. Okay, so again, the secret sharing is defined by a graph, a bipartite graph of this form. And it says that the left party and the right party should be able to reconstruct only if they are joined by an edge in this graph. That's a graph access structure. It's really what's also called a forbidden graph. So to be technically correct, I should have called it a forbidden graph access structure, but okay, fine, but that's what it is. Okay, so really there's a correspondence between sort of this access structure and functions. So, so you should think about the edge x comma y being in the access structure if and only if so the adjacency function evaluates to 1 on x comma y, right? So this is the correspondence that we talked about. Okay, so this is the graph access. So now I claim that if you have a CDS scheme, you immediately get a secret sharing scheme for graph access structures. The question is how? Okay, so here it is. In a secret sharing scheme, again, there's a dealer, right, who has a bit B, and he has to do something to generate shares. How many shares? 2 times capital N shares, give it to each party on the left and the right. That's what he wants. Okay. So what does party X on the left get and party Y on the right get? So here's what the dealer does. He samples a random string R, right? He has this bit B, and he computes all possible Alice messages on all possible X's, and he computes all possible Bob messages on all possible Y's. Okay? And he gives the corresponding messages to the parties on the left and the right. Yeah, that's that. Yes, that's it. So now, why is this good? Because imagine two parties coming together from the left and the right, right? Parties X and Y. Party X has the Alice message on X. Party Y has the Bob message on Y. And CDS tells you that they can reconstruct only if the function f x y outputs 1, and the function f is really the adjacency function, so exactly corresponds to graph signature. Okay, so some of you at least might be wondering, oh, what about two parties coming from the same side, etc., etc. But these all turn out actually to be completely trivial, and they can be handled. And I don't want to. So it's an exercise offline. Okay, don't think about it now. Okay, so that's CDS and secret sharing. So clearly there's a strong connection between sort of CDS and secret sharing. Okay, and looking down the line, what we want to do is we don't want this forbidden graph. We don't want graphs. We don't want nothing. We actually want like secret sharing for all possible access structures. So that's going to be our goal. Okay, so that's what we'll do. And let me actually make the problem harder for myself. Okay, isn't that fun? So I'm not going to sort of think about sort of Alice having an little n-bit input and Bob having a little n-bit input. Alice actually has an entire truth table, right? So that's called a database D, which is the same as a truth table for an little n-bit function. And Bob, same thing as before, right? He has an input to this function. Okay, this is harder than before because any protocol that solves this can actually solve the setting where Alice has a single bit, so she writes down the truth table for the residual function, and then you're good. Okay, so this is actually the harder problem. Yeah, good. So now the goal is that Charlie, there's no public function. Rather, Charlie should be able to, Charlie knows both the truth table D and the input X, and he should be able to recover the bit B only if D of X is 1. In other words, the truth table says 1 on this input. Okay, so this is super important that we actually understand this primitive. So let me ask if let me pause for 15 seconds and see if there are any questions. All good? Okay, I will do 15 seconds. All right, good. Let me keep going. Okay. All right, so that's what it is. And now we could ask, look, what do we know for CDS? Like, what kind of protocols do we know? It's not completely. Well, actually, it's an exercise to construct sort of some protocol that solves CDS regardless of the communication complexity. And I'll actually tell you one of the solutions today, and I recommend that you go back and try to figure out the rest of the solutions by yourself. Okay, so the upper bound, the best upper bound is 2 to the n over 2. All right, so again, 2 to the n is the size of the truth table. So 2 to the n over 2 communication, you can actually figure things out. You can actually do this solve this problem. The best lower bound is omega n. So again, you see this sort of exponential gap sort of phenomenon happening. And both are sort of, I think, the lower bound is the work of Gay, Karanidis, and Wee, and the upper bound also that work, I think. Okay, so this is all very mysterious. So let's actually do a protocol. Okay, so let me actually tell you how a protocol works. So yeah, this is the problem. CDS, you have Alice has an n-bit 2 to the capital N, 2 to the little n-bit database. Bob has and so on. Okay, so what can Alice send? Here is a protocol. Alice actually thinks about the random string, the shared random string with the common random string with Bob, as a sequence of capital N bits, R1 up to R capital N. And she just picks out those bits that correspond to the 1 entries in the database, right? Just picks out those bits and uses that as a one-time pad for the bit B that she wants to communicate. Okay, so she encrypts the bit B using a subset of the little r's. Which ones? Well, the ones for which the database entries are 1. What does Bob say? Bob just looks. Bob has an index X. He says, go, let me look up this capital R for the right bit, R sub X, and send it over to Charlie. Okay, that's that. So you see what's going on, right? If the database on index X evaluates to 1, rather the database entry on index X is 1, then Charlie has both R sub X, and he also has R sub X XORed with B, and then he gets B. And if D sub X is 0, then he just does not have, R sub X XOR B at all. And then he has no information about B at all. Okay. So this is a protocol where, what is the communication complexity? Alice sends 2 to the n, 2 to the little n bits in the worst case, right? And Bob sends 1 bit, a single bit. It turns out it's a little bit less trivial to show a protocol that has opposite guarantees, where Alice sends 1 bit and Bob sends 2 to the little n bits. And it turns out, as I think Hotek and friends showed, that you can actually do a balancing trick between the two. You can actually make both of them work hard. And in fact, both of them send like 2 to the n over 2 bits. Okay, so that's the state of the art. And a curious feature of all these protocols is that they all have linear reconstruction. In other words, Charlie has a linear function that depends on D and X, his input, that he applies to the Alice and Bob messages. So it's a linear function on the Alice and Bob messages that lets him reconstruct, that outputs the bit B. Okay, so that's the feature of these constructions. In fact, Hotek and friends showed that for any protocol, any serious protocol with linear reconstruction, the size of the Alice message times the size of the Bob message has to be 2 to the n. In other words, they actually constructed an optimal protocol, right? I mean, if you stick with linear reconstruction, there is nothing you can do for CDS. Okay, so that's what they showed. So, our line of thought is we want to do secret sharing. And to do that, we want to construct a better CDS protocol. And here you go. You cannot reconstruct a better CDS protocol if you stick with linear reconstruction. So what do? You do nonlinear. You sort of try to go to nonlinear reconstruction protocols. That's precisely what. Okay, so here is our theorem. There is a CDS protocol with total communication 2 to the square root n bits, as I said before. In fact, we show not just a single CDS protocol, we show a transformation from 2 server private information retrieval protocols, information-theoretic private information retrieval protocols, into a CDS protocol. And we can't start with any PIR protocol. We have to start with a nice enough PIR protocol. But it turns out that all known PIR protocols, to the best of my knowledge, are nice enough. So, like we can take all of them and put it through our compiler and get new CDS protocols. Okay, so that's what I'm going to show. That's actually, I have about half an hour, and that's what I'm going to sort of really focus on. Okay, so I said we start with the PIR and construct CDS, and therefore secret sharing and so forth. But where does this all come from? Like, why did we go to PIR schemes to begin with? Right? So, the high level sort of picture is, what we are trying to do is solve the communication versus computation trade-off. Right? We want to make communication independent of the computational cost, or at the very least, strictly smaller than the computational cost. And you start asking, has this been done before? Can we stand on the shoulders of giants? Has this problem been looked at and solved before? Indeed, the answer is yes. In the computational setting, where you have computational security, so maybe I should just kind of briefly mention this because this is IT crypto conference. FHE, homomorphic encryption, and the new kid on the block called function secret sharing actually do give us low communication MPC protocols. So the communication is independent of the smaller than the computation size, right? So that We know how to do it, but we're not in the computational setting. We're in the information theoretic setting. And there again, we know sort of solutions to this problem. In fact, private information retrieval can be thought of as a way to sort of do multi-party computation. In fact, that was made precise in a work of Eyal and Yuval back in 2004. It was a beautiful paper. So you can solve private information retrieval with communication complexity less than the database or the truth table size. In other words, less than the computational representation of a function at hand. Okay, so this we know. This we actually know. So that's actually a very good thing to start with. In fact, even better, the work of Amos, Yuval, Ranjit, and Eyal that showed how to take any super duper nice peer protocol and turn it into what's called a PSM protocol, which is closely related to but stronger than CDS. And you know, that's actually nice too. So we are actually getting, this is getting hotter and hotter and hotter. Okay, so yeah. But you know, in their work, they needed this super duper nice protocol, and not many protocols are super duper nice. In fact, the best known peer protocols are not super duper nice. Okay, so we can't, you know, so there's a little bit of a sort of a, yeah, super duper is too nice. We don't want to be too nice. We just want to be nice enough and get things done. Okay, so all these give you indication that, you know, peer really is the right thing to look at. You know, there is something going on there and we should be looking at it. Okay, in fact, let's look at it. So what is private information retrieval? Let me sort of define it at the, you know, for all the suspense, actually define it. So here again, there is an Alice and a Bob. And the Alice and the Bob, they both have the same database, right? So that's not the case for CDS. They have the same database D. Charlie has an index X, and he sends, he wants to sort of actually get the Xth index of the database, Xth element in the database, without actually telling X to either Alice or to Bob. So what he does is he sends a query Q0 to Bob and Q1 to Alice, and gets sort of an answer. And from this, he can reconstruct D of X. But this protocol shouldn't reveal any information. Neither Alice nor Bob alone can learn any information about the index X. Okay, so this is what PIR is, and this is an amazing primitive worth knowing. Okay, the best known two-server peer, recent work, still stands, has communication complexity 2 to the square root n. That was after a long sort of line of work, long line of work. So you start thinking, you know, so don't look at the bottom half of the slide, just look at the top half for the moment. You know, from the 50,000 feet view, you know, they're both the same, right? I mean, you know, there's an Alice, there's a Bob, there's a Charlie, and there are sort of things coming sort of one way. There's a little bit going in the other way in peer, but whatever. Okay, so they look very similar, right? But, you know, you come down to like 10,000 feet, and that stops looking similar at all. In fact, in peer, you want to hide the index, which is in little n bit string, and CDS, you only want to hide a single bit. So that actually seems easier. In peer, you don't have common randomness between Alice and Bob, because I suppose they're not trying to hide anything from Charlie. So, you know, why do you need it? And in CDS, you have a common random string R. Actually, should also make life easier. In peer, the databases are replicated 2 ways. And there is no replication in CDS. In fact, it's more like a number on the forehead type situation going on in CDS, right? So they look, you know, 10,000 feet, they start looking completely different from each other. Okay, so you start thinking, start questioning your sanity. Say, you know, am I really going nuts trying to connect the two? But then you look again and say, well, you know, there is smoke, and when there is smoke, there must be fire, right? What is the smoke? The best lower bound for peer is omega n, and the best upper bound is 2 to the root n. You know, in CDS, the best lower bound is omega n, and the best upper bound, for a while, the constructions looked a lot similar to the peer constructions. So then you say, okay, you know what? You start wondering, okay? Start chasing the fire, chasing the smoke, hoping to find fire. Okay, all right, so that's what we do. Okay, so that's, I set up a whole bunch of sort of suspense. Let me actually jump into the construction. In fact, the construction will be 1 slide. Okay. In fact, there will be very little math, and there will be pictures on the slide. So here's the construction. You start from a peer protocol. You want to construct a CDS. That's the goal, right? A peer. There are queries. There are answers. So in fact, this is a 2-round, 2-message peer. But okay, that's what we want. All right, so how do we start? First, I'm going to split Charlie into two Charlies. Okay, there's a query generating Charlie, and then there's a reconstructing Charlie. They both share this randomness, so they can sort of, they know the same sort of thing. Yeah, so that's sort of a syntactical thing. And now I want to look at Charlie, the two queries that he sends, Q0 and Q1, right? And I say, Q0 and Q1 together should contain information about X, should actually completely determine X. And yet neither Q0 nor Q1 has any information about X. So what does that start smelling of? That smells like a secret sharing of X. In fact, it doesn't have to be X. In fact, Charlie can pre-process X into some longer string called use, right? Which has all the information about X. And then he takes this and secret shares it into Q0 and Q1. So that's what it looks like, right? Okay, they call it that. So R is a random string, R plus use of X, they together form a secret sharing of use of X. Okay, so that's so far syntactical. And now, again, this is syntactical. What do the databases do? They apply a function on the incoming queries, right? The left database applies this function called H sub D. H is a function that depends on the database. You apply it to R, you generate an answer. So nothing, this is really like a notational kind of thing. Also, the right guy, he applies HD to the incoming query, which is R plus use of X. Okay, so far so good. All right. And now comes the sort of the nice peer part of things. What I want is that the reconstructor, the Charlie, the half Charlie in the bottom, should be able to apply a linear function on the two answers, namely HD of R and HD of R plus UX, and reconstruct the database, the database entry, namely T sub X. Okay, so that's what I want. I wrote down on the top right a particular form of this linear function, but it turns out that doesn't matter. Any linear function can actually be written down in this way. Okay, so again, let me reiterate. There is a linear function that depends on Charlie's input X, that when you apply to the two messages, incoming messages, should give you the database entry. That's what it is. Okay, and we'll call this, we'll give it a name. We'll call this a linear client PIR scheme. Okay, that's a property. So far all sort of generic except this property which we will need. All right, so okay, fine. So now what? Okay, so I want to go to CDS. Okay, so what happens in CDS? There is an Alice, there is the Bob, and then there's a Charlie. Right? So who is Alice, who's Bob, who's Charlie? Well, Alice actually knows the database, yes? So it makes sense that this guy, the left database is Alice. Okay, so that's good. Bob knows, well, the other way around. Bob knows that, yeah, mixed Alice and Bob. Bob is the left database. Alice knows the input X, and therefore she is one half of the top half of Charlie. Okay? I'm just pattern matching at this point, okay? And all makes sense, right? Alice knows her input X and generates a message, it sends it out somewhere. Bob knows the database, it generates a bit, it generates a message, sends it out somewhere. They also need a common random string, but here it seems like Alice is actually sending a message to Bob, which is not permitted in CDS at all, right? There's no message between Alice and Bob. But this message is a random string. So there's no message, it's really a common shared randomness, that's it. So now we're getting closer and closer. Yeah, it's looking warmer and warmer, right? Okay, so now all good. Who's Charlie? Charlie is really, okay, so let's go back. So Alice actually holds an input X and a bit B, right? So because Charlie actually, at the end of the day, the CDS Charlie knows both the database and the input. The only thing he doesn't know is bit, and there is no bit here. Where is a bit? So here's what we are going to do. Alice does one of two things depending on her bit B. She either sends the peer message R plus UX if the bit B is 0, or if the bit B is 1, sorry, or she just sends the randomness R if the bit B is 0. So in other words, she sends R plus B times use of X. So either plus use of X or not, depending on the bit B. Okay, that's what she does. That's how she incorporates the bit B into her message. Now let's rewrite the equation on the top right and say, well, you know what? what's being sent out is not r plus u sub x, but really it's r plus b times u sub x. Okay, so what happens here? If b is 0, right, then this equation is actually 0, identically 0, right? Because on the left you have hd of r plus 0, which is hd of r, minus hd of r, 0, right? Yeah, does that make sense? If b is 1, then it is actually d sub x. So concisely, if you try to write it down as a function, the right-hand side, when you evaluate it, it's b times d sub x. So in other words, if d sub x is 1, it's b. If d sub x is 0, it's a 0 always, right? Yeah, that's good. So again, warmer, even warmer. Okay, so now I'm going to do the best work on my slides, which is this animation. You know, so now I say, okay, you know what? Now I have my Charlie. Now I have my Charlie. Who is the Charlie? The Charlie is 1/2 of the database. Remember? Yeah, let's do it again. Okay, why not? So 1/2 of the database, the right half of the database, together with the bottom half of the peer Charlie, is my CDS Charlie. Okay. Does this make sense? How does this make sense? Charlie gets these 2 messages from Alice and Bob, right? What does he need to do? He needs to compute that equation on the top right. Okay, so he computes HD on the Alice message, which he can because he knows D. He knows HD of R from Bob directly, and he knows U sub X because he knows X. He can compute U sub X. Because he really uses knowledge of both D and X. He computes this equation and he gets what he wants. He gets B times D sub X. It's exactly what he's supposed to get. Right? D sub x is 1, he gets b, otherwise he gets 0. Okay, that's it. That's the CDS protocol. Well, that's if you only care about correctness. Okay, now you have to I have to actually prove that this is private as well, in the sense that if d sub x is 0, Charlie does not get, these 2 messages don't give Charlie any information about b. That's what I want. That's the one other thing I want to prove, right? Why is that the case? Well, look at the Alice message. Okay, so what is Alice message? It's b times something. So it has some information about b, but one-time padded with r, right? You add r to it. What is r? R is a truly random string. So Alice message by itself is completely random, right? Bob's message, on the other hand, actually reveals some information about this randomness. So you know, I have a one-time pad, but I do have one-time pad encrypted b. But I have some information about the pad, so not clear, right? Not clear anymore, not clear at all. So it's correct, but not private. But it turns out that this is actually not that hard to fix. And again, to fix this, we go back to the linearity of this scheme. We can sort of, you know, do the one-time pad trick once again, adding more randomness to the common random string. You know, this offending message from Bob, that's the one that reveals information about R, you one-time pad it as well. Okay, and then nothing reveals any information at this point, right? But then correctness goes down the drain. But you know, all you need for correctness is actually some little bit of information, which is the new one-time pad in a product with U sub X. And that really, I'm using the linearity of the scheme to achieve that. So it turns out that, you know, put together, this sort of non-privacy issue is pretty easy to handle. And using the fact that reconstruction is a linear function. Okay, so that's the scheme. At this point, I claim you have a correct and private CDS scheme starting from any linear client PIR scheme. The one thing, let me say one more thing, and then I'll actually pause for questions. The one thing I want to say is, you know, well, actually 2 things. One, the communication complexity is more or less exactly the communication complexity of the peer scheme, which is 2 to the root n. There's a little bit in addition, but that's sort of negligible compared to 2 to the root n. So we got a CDS scheme, right? Starting from a linear client PIR scheme, right? So, you know, the question is, did we get a linear Charlie, linear client CDS scheme as a result? And if we did that, there must be something seriously wrong, because Hotek and friends proved that you can't do better than 2 to the n over 2 communication for linear client CDS. So what exactly is going on? One could sort of look deeper into it. The point is that the CDS Charlie is actually not linear. The CDS Charlie, to do the animation once again, is an amalgamation of the peer Charlie, which is linear, and the peer database, which is highly nonlinear. Okay, so that's how we sort of used, even though the peer scheme is linear clients, we can still use it to get a nonlinear CDS scheme. Okay, so that's what the scheme is. Let me, okay, actually, let me say one more thing. The instantiation, I'm not going to say too much about it. There is there's a beautiful work on peer that in turn sort of goes into amazing mathematics that comes from matching vector families. And that actually is what lets us instantiate a linear client PIR scheme with this good communication complexity. Once you put this together, you get a CDS scheme. So let me kind of go back to the previous slide. Let me pause for 30 seconds. Okay, let me take a couple of questions maybe.
We know there's a question from Yael. It was answered.
Oh, yeah, I got it. It was my mistake.
No, I think it's asked it for the entire audience.
Yes.
It's a good idea. Yeah.
Yes.
Yeah.
If you want to ask.
Sorry, yeah. Oh. Yeah, sorry, I was just confused about what you learn is actually D sub x, and I was confused about, you know, you wanted to learn B, not D sub x. But it was my bad. You actually learned B times D sub x, which is exactly what you want to learn. So we're good. But Vinod, can I ask you one question, which is, so is the scheme, the peer scheme, you went through it really quickly just now, but is the peer scheme of Dvir et al. Is the one that has the property, the linear property that you want, and therefore you can kind of convert it here. Is that what you said, right?
Correct. That's correct. That's correct. In fact, all the peer schemes, starting from the work of Eyal and Shor, Goldreich, Kushlevitz, Sudan, they all seem to be linear clients, to my knowledge.
We know that I have a counterexample. Al and I have a scheme where the reconstruction depends on the randomness.
Interesting. So which scheme is with who again?
It's something that depends on the polynomial polynomial. So you'll know the randomness to reconstruct a secret, and the randomness is part of the shared randomness, not to Charlie in your scenario.
I see.
It won't give anything more important, but you cannot. It's not nice according to your definition.
Great. Sounds good. Sounds good. I'll ask you offline, and I'd like to know more. Okay, good. So most peer schemes are nice. Okay, so let me keep going.
I think there's another question in the chat, I believe.
Yeah, go for it.
So in the peer to CDS transformation, how does Bob know how many bits of random tape to use?
How does Bob know how many bits? So the number of random bits is the length of the random tape is predetermined. That's a short answer. It's predetermined. It's like 2 to the n plus like the length of R is 2 to the n. It's 2 to the n random bits. R prime is whatever it is, length of HT of R, which is again predetermined. Yeah. Okay, sounds good. Can I? I'll keep going. Okay. All right. So we constructed a CDS. So that was really the step one. That's really the much of what I'm going to talk about today. Let me briefly say how I do steps 2 and 3. Step 2. So CDS, as we saw, gives you a secret sharing scheme for graph access structures. The first sort of generalization that we do is, instead of again, you have 2 groups of parties, right? And interesting sort of authorized subsets come from taking one party from the left and one party from the right? They're pairs of parties. Of course, I could generalize this to not 2 groups of n over 2 each, but n over 2 groups of 2 parties each. Then the authorized subsets will look at sort of one party from each pair of parties, right? So they will be sort of n over 2 size sets that are constructed by taking one out of each pair, right? So this is you can define it as a hypergraph if you would like. And that sort of dramatically expands the number of access functions, as you would expect. And now you have 2 to the n over 2 access functions that you can sort of write it this way. The question is, I want to do graph secret sharing using CDS. I want to do hypergraph secret sharing, what I did to graph secret sharing, and I want a generalization of CDS that does the right job. And that turns out is a multi-party CDS. So what is a multi-party CDS? Again, 2-party CDS, there's an Alice and a Bob. Bob actually holds the entire index X, the entire database index X. What I want to do is I want to split Bob, let's say, into 2 parties where the left Bob has 1/2 of the index and the right Bob has the other half of the index. But in fact, I could do this. I could really completely decompose Bob. I could have n Bobs, but each Bob has 1 bit of the index, and that's the setting, right? So there is 1 Alice who holds the database, there are n Bobs who hold 1 bit each of the index, and they want to do the same thing as before. Okay, and we show that again you can construct a multi-party CDS protocol with communication complexity 2 to the root n bit. So going from CDS, the 2-party, to the multi-party did not cost us anything at all. There's a little sort of cost in the exponent, logarithmic cost in the exponent, but never mind. Essentially, it costs nothing at all. And again, for the linear reconstruction case, we construct a multi-party CDS protocol with total communication 2 to the n over 2 bits, and that actually turns out to be optimal. This was also observed by Amos and Nati concurrently. Okay, and the corollary do the same trick, so going from CDS to graph secret sharing to the hypergraphs, you get a forbidden hypergraph secret sharing with the same parameters. Okay, so let me say one word, one sort of slide about how we go from 2-party to multi-party CDS. And we want to lift again a 2-party CDS into n-party CDS. And a natural idea to do this is to do what's called player emulation. In other words, the n Bobs emulate what the 1 Bob did in the 2 CDS. And yeah, that's what we want to do. But that seems like actually like a chicken and egg problem, because I'm actually asking all these n Bobs to do a potentially complex computation, but that's sort of harder than the problem that we were going to solve to begin with. So it seems like there's a chicken and egg issue here. The way we solve it is to observe that Bob's computation in the 2 CDS scheme, which again comes from the Dvir-Gopi protocol, which again comes from the Grolmusch sort of matching vector methodology, matching vector construction, is actually pretty simple. So we look non-black box into our 2 CDS, and therefore going down all the way to matching vector, we say Bob's computational complexity in the 2 CDS is pretty small. In fact, it can be written down as a branching program, small branching program. And therefore you can use sort of standard sort of tricks to do this player emulation, and that's what we do. What I said is not completely correct. If you go all the way down to Grolmusch, you don't actually get such simple matching vectors. You actually have to change Grolmusch a little bit. So it's really very highly non-black box to get this result. Okay, so that's how we do. One brief sort of slide on how we get multi-party. If you remember nothing from it, just remember you do player emulation, which is sort of what you want to do. Emulate sort of the 1 Bob with n Bobs, and we can do a good job of it if the computational complexity of Bob is small, and that's what we sort of we make that happen. That's what we do. Okay, so that's the multi-party CDS. And finally, step 3 is going all the way to secret sharing schemes for arbitrary access structures. And I'll say even more. I'll be even more brief. I'll be just as brief about it. So it turns out that the first step is actually pretty simple. Forbidden hypergraphs actually look at certain subsets of n over 2 parties. In fact, you divide parties into pairs. You say, I'm going to pick 1 from each pair. That's the set of access structures that you support. You can slightly generalize it to access structures, slice function access structures, which says that any set of more than n over 2 parties is authorized, right? Any set of less than n over 2 parties is unauthorized. And really, in the middle, for n over 2 parties, you can do whatever you want. It could be completely arbitrary. That's called a slice function. And that's sort of an even larger class of access structures than forbidden hypergraphs. In fact, there's 2 to the right. I mean, in the middle, there are n over 2 parties, right? And if you sort of compute the number of access functions, it's really 2 to the n choose n over 2. So it turns out that there's a way to turn generically forbidden hypergraph secret sharing into slice function secret sharing and preserving communication complexity. So far all we did actually stuck with the 2 to the square root n communication complexity, which is really what we want to get in some sense. It's the last step that goes from slice functions to general functions that completely ruins this, this very nice story. And that's where we go from 2 to the square root n to 2 to the 0.994. So I'll say one word about where the 0.994 comes in. And here's what happens. So what I want to do for general access structures, I want to take an arbitrary monotone function. I want to write it as a combination of what I know how to do, right? And what do I know how to do? I know how to do slice functions, and I know how to handle sort of small enough access structures, in the sense access structures that have few sets. In fact, what we end up doing is we split an arbitrary monotone function into sort of a slice function and monotone functions that are only non-trivial on sets of size more than n over 2. Like we call this f top, and another function which is only non-trivial on sets of size less than n over 2 we call f bot. So it turns out there's actually a precise way to define these things, and there's a way to write an arbitrary monotone function in this as a combination. And more than that, you can actually use secret sharing schemes for these 3 access structures put together to construct a secret sharing scheme for f itself, with the complexity being the sum of the complexities of these things. The unfortunate sort of wrinkle in this idea is that f bot and f top are actually pretty large. So f bot really, for example, handles all sets of size less than n over 2, of which there are a lot of them, right? The number of sets of size n over 2 is 2 to the n over square root n, and the number of sets outside is 2 to the n times 1 minus 1 over square root n, which is quite large. So you cannot do something trivial for those things and get away with it. Again, even more briefly, the way we solve it is we extend sort of slice function secret sharing to sort of secret sharing schemes for thicker slices. So you should think about slice function as a slice of width 1. You can extend it to sort of width sort of delta n, or 2 times delta n in this picture. And again, the same sort of methodology goes through. And now you have a trade-off. The larger the delta, the costlier the thick slice, the thicker the slice, and therefore the costlier the thick slice secret sharing. But the rest of it is smaller sets, and therefore the cheaper, the trivial, the f bot and f top secret sharing. So now you can sort of play balancing games, and we get sort of 0.994 by playing this balancing game. Amos and Benny and others improved this to 0.8 something by playing the balancing game more cleverly in a recursive way. The recent work of Amos and Benny and others again, depart from this methodology and consider a more general form of CDS called robust CDS. That again sort of gives them an advantage in this constant. Okay, so summary, what we had was secret sharing schemes of this nature. And one thing I do want to say is that a corollary of our linear secret sharing scheme, which shares size 2 to the 0.999n, is a purely computational corollary. So, Karshner and Vigdison showed a tight connection between computational complexity of linear secret sharing schemes and the size of monotone span programs that compute functions. And as a corollary of our secret sharing scheme, we show that every monotone function has a monotone span program of size 2 to the 0.999 times n. So it's a purely computational, it doesn't talk about communication complexity at all. It's a purely computational corollary that we get out of this bounding the communication complexity. Okay, so I'll sort of finish with that. I'll take 2 more minutes. So the picture is, the new picture is this with all the new works that build on top of our work. For unrestricted secret sharing, lower bound hasn't improved from the 90s. The upper bound is now 2 to the 0.637n. Linear secret sharing, 2 to the n over 2 is the counting lower bound, and the upper bound is 2 to the 0.762n. So open problem, this sort of immediately suggests an open problem. In fact, I believe Amos's conjecture is that for general secret sharing schemes, you need the shares of size 2 to the omega n. In other words, log s over n is omega 1, is Amos's sort of long-standing conjecture, and it's a great problem to prove Amos wrong. I don't believe there is any money on it, but there's prestige on it. Okay, so that's the first open problem. If you want an easier open problem, here is one. So we said, linear secret sharing schemes can only do so well. They can only do 2 to the n over 2. And at this point, current state of the art, doesn't tell us that nonlinear secret sharing schemes can do better than every conceivable linear secret sharing schemes. We can't conclude that because, the complexity is more than 2 to the n over 2 for the unrestricted secret sharing. So that's the question. Can nonlinearity provably buy us more? That's the question of showing that the shared complexity is less than 2 to the n over 2. That's, again, a fantastic open question. That's easier than actually proving Amos wrong, but it's a great open question. If you really want to go all the way, you want to really close the upper and lower bounds for general secret sharing schemes, and there I would conjecture an upper bound of polynomial in n. I'm mindful of the fact that this is being recorded, nevertheless I'll say it. Let me step even further back. So this sort of work fits into the general theme of sort of computation versus communication cost and various problems related to secure computation. There's lots of very interesting work on it. CDS, PIR, secret sharing we saw. Private simultaneous messages is yet another problem, which is very interesting, MPC. And there are all sorts of sort of connections that are being formed right now between these primitives. Some sort of solid arrows which say, anything of this nature gives you that. Dotted arrows that say anything of this nature with some properties, niceness or super duper niceness gives you something else. So I think there's a lot more to be discovered here, and I think it would shed new light on sort of really foundational problems, not just in cryptography, but also in sort of coding theory and sort of other fields. Yeah, so that's lots to do here. Thank you very much.
Thanks, Vinod, for a lovely talk. I don't see any questions. Adam, you had some comment?
Oh, not an important one. Just what Vinod described as an easier problem could be harder. Namely, if the actual lower bound is 2 to the n over 2 for right for general secret sharing scheme, then proving Amos wrong would only require right.
No, proving Amos right is
sorry. Proving Amos right might be considerably easier than proving lower bound of the form.
Well, what can I say? I mean, I'm an upper bounds guy. You're right.
So I think, Vinod, another interesting question is to design better private simultaneous messages, basically
yes,
taking all these improvements to PSM protocols.
Yeah, absolutely. Yeah, that's yeah, absolutely. I guess now that I'm on it, maybe another question is. Another question is the following, right? So far we've been talking about sort of general secret sharing schemes. Like we want to capture all access structures, blah 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 blah, right? Or very large class, most access structures, etc., etc. What about can we turn the results we prove in these high regimes and go down to earth and show better access structures for better secret sharing schemes for concrete access structures? I think that's a great sort of open question. And one of my sort of favorite things, which I sort of read about it for the first time from Amos and Yuval's work, I think, or one of the sequence of works, is a directed graph access structure. So rather connectivity in a directed graph sort of access structure. You can sort of build an access structure out of it, and and again, okay, so let me say what it is, right? So you have n choose two parties corresponding to all possible edges. Rather, let's say 2 times n choose two parties that correspond to all possible directed edges between sort of nodes, and a subset of parties corresponds to a concrete graph. Right, the subset of parties says this edge exists, this edge doesn't exist because it corresponds to a concrete graph. The question is there a path from a designated source node to a designated sink node in this graph? If yes, you say this set is actually an authorized set, otherwise you say no. And for this, we don't know a polynomial size secret sharing scheme with polynomial size shares. This is in contrast to undirected graphs, where there is a very simple secret sharing scheme with polynomial size shares. There is a very, very interesting questions for concrete access structures, which are interesting.
So I encourage all the speakers, all the audience to ask.
Yeah, this is the thing, right? I mean, if you let me speak, I'll keep speaking. So if you don't want to hear me anymore, please.
So Vinod, I have a question. Sorry. So I have a question. Just, is there any sense of how far this type of connection to peer can take you? For example, are there any lower bounds on these peers with linear client or anything like that? Or can you even hope that it will take you to polynomial share size?
So I haven't looked into it that closely, but I'm not aware of any lower bounds on linear client peer schemes. Maybe one of the people who know better, like Amos or Yuval, can correct me. I'm not aware of any lower bounds. Yes. Adam?
I had a question about your last slide. So I don't remember the exact statement, but I remember, Nissim and Noah and Nissim have an old result, I mean, relatively old result from maybe 2000, showing that for a general transformation from communication limited, non-secure protocols to, if I remember correctly, two-party computation of the same functionality with a related communication boundary. And so like, roughly a transformation to multi-party, two-party computation that has, that is mostly bound by the communication cost of the original thing rather than its computational cost. I don't remember the exact statement, and I might be misstating it. But is there any obstacle to a general statement of that form? Let me pose this as a question: is any obstacle to a general statement that says if you start with a non-private communication protocol that computes some function using, C bits of communication per party or something like that, to turn that into a multi-party computation protocol with some related communication, maybe plus some additive overhead that depends on the number of parties or something like that?
So, so the thing is, right? If you only care about sort of non-private, so non-private communication complexity is only interesting up to the input size, right? Because if you can communicate the input size, it's you can sort of you can trivially achieve what you want to achieve.
Right.
Whereas here, it's far from trivial. The input size is far from trivial. In fact, the trivial thing is 2 to the input size, right? And that's what all these sort of peer works sort of include.
I see.
General transformation has to blow up the communication complexity, or it's doing something something that we don't know how to do at this point. I guess one other way to sort of, let me answer your question slightly differently. There is a result of, I believe, Eyal and Yuval, who show how to construct a secure multi-party computation protocol for any function using peer protocols. So the idea is that peer is actually kind of a secure to 3-party computation protocol where the database is like the truth table, et cetera, you can actually make it into a secure 3-party protocol, for example, with in the normal sense that we think about it. It's not like, I can't communicate and you can't communicate. Really, like, you can do it. But the communication cost there is basically the same as the peer cost. So I think the bottom line is that somehow, if you think about non-private protocols, they don't need to talk about computational cost at all, right? And that's why you have the trivial input size upper bound. And for privacy, it seems like so far you do need to talk at least a little bit about the computational cost. And that's, and removing that is really the problem. That's really is the holy grail, right? So I guess, I guess maybe Adam, you actually asked the hardest problem of this entire talk and probably the entire area. I don't actually know the result of Naur and Nisim that you're referencing. Maybe I'll actually go back and look at it, but it cannot be this. That's I'm pretty sure of.
Okay, so since the time is over and there's no more questions, so thank Vinod for a lovely talk. And we'll convene in 15 minutes time, Adam?
That's right. So the next session starts at noon Eastern. So I guess 4 p.m. UTC.
Thank you very much.
Thanks, Vinod. Great talk.
Thanks.
Thank you.
Adam, should I
Yes.
try sharing? Should I try sharing my slides or?
Yeah, here, I'll
leave it
turn off
alone?
mine. Go ahead and share yours and just check that. I can hear you well, by the way. So your
Oh,
sound.
okay, great. And I guess I want to also check if I can use the, yeah, I have access to all these tools, so I can use like the spotlight. Oh, no. Yes, okay.
Yeah, that looks great. So why don't we put the splash screen back up just so that
Oh,
people
okay.
who log in know when we're going to restart?
Okay.
So do you want to
stop share? Yeah.
turn your sharing on, and you can always turn it, turn it back on.
Okay, sure.
Hello.
Hi, Stefan.
Hi.
Hey.
You hear me, right? Okay, good. So it's an hour and 15 minutes, right? Or should the talk take 1 hour and then we take 15 minutes questions?
Yeah, that's right.
An hour and then 15 minutes question. Okay.
Yeah, and you can take some questions online if you see there's
Yes.
sort of a pressing question. You can stop Dana, but otherwise, I recommend Dana that you don't check the Q&A
Okay.
box or the chat box. It's too distracting for you to check it during the talk.
Yeah, I know that from teaching on Zoom. It's really
Yes.
distracting.
So I will be looking at it, and if there is some urgent question, then I will interrupt Dana, but otherwise the questions will be asked
Okay.
in the
Or I
last
can
15
also
minutes.
try to stop
Yes.
at different points.
Okay. Panelists and attendees.
So Stefan, I made you a co-host, so you can unmute people also
Okay,
in
good.
the Q&A if you want them to talk.
Good. Thanks.
So Donna, why don't you go ahead and share your slides?
We'll be starting, right?
Okay, and yeah, are you ready? Are you ready
Yes.
to start, Donna and Stefan? Are you the chair?
Yes, I'm ready.
Yeah, I'm ready.
So I will start the recording, and then you guys can take it away.
It is my pleasure to introduce Dana Dahmat-Solet from the University of Maryland. Dana did her doctorate under Tal Malkin at the Columbia University. She was then a postdoc at Microsoft Research New England. Dana has published a number of papers on several aspects of cryptography, including secure computation and security against physical attacks. Her today's talk is about non-malleable codes, which is one of the tools used in the area of the foundations of the tamper-resilient crypto. So please welcome Dana.
So thank you, Stefan, so much for the introduction. So today I'm going to be talking about a sequence of works that finally led to non-malleable codes for AC0. And I'm going to be highlighting two of the results along thank co-authors on those two papers covering, and those are Marshall Ball, Xiao Guo, Mukul Kulkarni, Tal Malkin, and Ling Tan. Okay, so let's start out with some background on coding scheme. Sender has a message X as input, and the sender is going to run the encode algorithm denoted by E on the message to obtain a code word. And then the sender will send the code word over a channel. The channel is going to select a function, little f, which we're going to call the tampering function, from some allowed class of functions, big F. And it's going to apply little f to the code word. The receiver is going to receive this tampered code word, and it's going to run the decode algorithm denoted by D in order to recover X tilde, which is the recovered message. And we want to have some guarantees between the relationship between the recovered message X tilde and the sent message X. And I just wanted to also note that this is a non-cryptographic setting. So know that there are no secret keys at all in this setting. The encode and decode algorithm are completely public, and they do not take as input any secret keys. So what type of guarantees can we expect to have about the received message? So the type of guarantees that we can achieve are going to largely depend on the class of tampering functions that we allow. So let's kind of look at the two ends of the spectrum. So on the one hand, we have error correcting codes, and these are going to achieve a very strong property of correctness. So we know that the recovered message, X tilde, is going to be the same as the message that was sent, X. However, we're going to have to restrict the class of functions f to only contain functions little f that modify less than distance over 2 code word symbols, where distance is the distance of the code. On the other end of the spectrum, we have non-malleable codes. And here we want to allow tampering functions f that potentially modify every code word symbol. In this case, we can no longer achieve correctness, but now the relationship that we're going to achieve between the recovered message and the sent message is going to be that either X tilde is the same as X or it's independent of X. And the desired property that we achieve in this setting is privacy. So specifically, one of the applications of non-malleable codes is to tamper resilient cryptography. So here we're going to encode the secret key of a device using a non-malleable code. And we're going to be able to guarantee that the secret key remains private even when an adversary can tamper with the encoding. So there's been a lot of prior work on non-malleable codes. This is a very active research area in the past several years. So non-malleable codes were introduced by Dembowski, Piaczek, and Wicks in 2010. And in that paper, they showed several results. One important result was that they showed that it's impossible to achieve non-malleable codes against all of P, against any polynomial time tampering. So let's see why this is the case. So remember that we are in a keyless setting. So there is no secret key between the sender and the receiver, and encode and decode are public. So if we have an efficient non-malleable code where the encode and decode functions are in P, then if we allow arbitrary tampering in P, what the adversary can do is it can simply decode the code word, change the message to a related message, and re-encode, and then forward this re-encoded code word to the receiver. And of course, we're not going to be able to achieve non-malleability in this setting. So this is going to be an important point that we're going to come back throughout the talk. And in this first paper, they also showed very strong existential results that show that you can achieve non-malleable codes against tampering classes of bounded size. So we know that the class of tampering functions F has to be computationally limited in some way. So what are the ways that people have looked at kind of limiting these functions F? So there's been a long line of works that looks at compartmentalized tampering families. So for example, bitwise tampering. So here, the tampering has to occur independently on each bit of the code word. Another popular class of tampering functions that people have looked at is split state tampering. So here the code word is split into multiple parts, and different tampering functions can be applied independently to each part of the code word. There have also been results on tamper resilience against permutations and bitwise tampering. And this is an example of a non-compartmentalized tampering class. So in this talk, I want to emphasize a more recent line of work that focuses on constructing non-malleable codes against tampering classes F that correspond to well-studied complexity classes. So I'm not going to go over all the results on this slide, but I just want to name a few of the classes that we can achieve non-malleable codes against, and I will go into more depth about some of these results. So these include bounded polynomial size circuits, various types of space-bounded tampering, and then NC0 and AC0, which are two complexity classes that I'm going to be talking about in more depth in the upcoming slides. So I want to draw your attention to the two leftmost columns here. And the reason for that is that the leftmost column is kind of the best possible setting. So in the leftmost column, we're going to consider information-theoretic constructions. So there are no computational assumptions involved. We're going to require that encode and decode are efficient, polynomial time. And we are in the standard model, so there is no CRS or random oracle. And prior to the work that I'm going to be talking about, it was known how to achieve non-malleable codes in this kind of optimal setting for NC0. For AC0, there was also a construction, also information theoretic, and in the standard model. However, there was a caveat, which was that the encode function was inefficient. So a message of length k would end up being encoded with a code word of exponential size in k. I also want to mention some of the subsequent work to our work, which continued on this path. So in kind of the optimal setting of information theoretic and standard model, it was shown how to get rate 1 non-malleable codes for NC0, non-malleable codes for bounded depth decision trees, and bounded degree polynomials. And on the other spectrum, where we require computational assumptions, although no CRS, together with co-authors, we showed how to get non-malleable codes for bounded uniform polynomial time tampering. So just to get ourselves familiar with some of these complexity classes that I'm going to keep mentioning throughout this talk, I want to kind of draw this visual picture here. So this outer circle represents P, polynomial time, and we know that we cannot achieve non-nullable codes for all of P. So we're going to be looking for classes that do not contain P, and we can try to construct non-nullable codes for such classes. And specifically, the type of classes that we're going to be looking at in this talk are classes that correspond intuitively to computations that take low parallel time. Okay, so more specifically, we're going to be considering various types of circuit classes. So first of all, the classes NC0 and AC0. So these are constant depth polynomial size circuits. In addition, NC0 requires bounded fan-in. So each gate has a constant number of incoming wires. And AC0, which is same as NC0, but has unbounded fan-in. So here we're going to allow any number of incoming wires in each gate. Another class that's going to be important to us is the class of local functions. So this is going to be the class of functions where each output bit depends on at most n to the 1 minus epsilon input bits. So each output bit depends on only a subset of the input bits. And finally, I want to mention the class NC1. So NC1 is a class of logarithmic depth polynomial size circuits. And actually, before I said that non-nullable codes for P are impossible, but non-nullable codes for NC1 are also out of our reach currently, because in fact, it is not known, we don't know how to show that NC1 does not contain P. We don't know how to separate NC1 and P with the current techniques that we have in complexity theory. And if NC1 is equal to P, then the impossibility results for P would apply to NC1. So if we want to restrict ourselves to constructions that are information theoretic and don't make any assumptions, then we can't even get up to NC1. We have to look inside or under NC1. And I also want to mention that there is, for the other classes that I mentioned, AC0, NC0, and local, there is actually an explicit function in P and also in NC1, which is not contained in these classes, and that is the parity function. So given an input string of n bits, output the parity of that string, that problem is outside of AC0, NC0, and local. So this gives us hope to be able to construct non-nullable codes for these classes. So prior work with co-authors presented non-nullable codes for local functions, which also includes NC0. And now the main result that I'm going to be talking about is the construction of non-nullable codes that are unconditionally secure against polynomial size and unbounded fan-in circuits of depth log n over log n. And the code length that we achieve is k to the 1 plus delta, where delta is a small constant between 0 and 1, where the input message is k bits and the output code word length is n. So I just want to note that this includes the class that we achieve includes the class AC0. It contains AC0. So remember, AC0 is a class of polynomial size unbounded fan-in circuits of constant depth. And for the case of AC0, our result actually gives a slightly better code word length of k to the 1 plus little o of 1. And I also want to emphasize that this result is essentially optimal in terms of circuit depth. This is kind of the best we can do in terms of circuit depth in the information theoretic setting. And this is because NC1, which I said we cannot construct non-nullable codes for NC1 without separating NC1 from P. And NC1 is contained in the class of polynomial size unbounded fan-in circuits of depth O of log n over log n. So if we increase the depth of circuits that we can handle in our result, then that would, if we substantially increase it, that would include NC1. So this is essentially optimal in terms of depth. And so here is a pictorial representation of the class that we can construct non-malleable codes for using this result. So this circle represents circuits that have depth log n over log n and polynomial size. I also want to mention a follow-up work. So I mentioned that our result is optimal in terms of circuit depth. It was not optimal in terms of circuit size. A follow-up work of Ball, Go, and Wicks presented non-malleable codes for bounded depth decision trees. And this is going to imply non-malleable codes for sub-exponential size and unbounded fan-in circuits of constant depth. Okay, so it's still constant depth, but now the size goes from polynomial to sub-exponential. And so pictorially, the follow-up work includes this purple circle. So everything from the prior result, and additionally, it includes constant depth and sub-exponential size circuits. Okay, so this is a good place to quickly stop for questions, if there's any questions.
I don't see any questions.
Okay, great. So I'll continue. So I'm going to start the kind of technical portion now of the talk, and I'm going to start by giving some definitions. So we gave some intuition of non-malleable codes, and now I'm going to give some formal definitions. So first, I'm going to talk about the syntax of a non-malleable code. So non-malleable code contains an encode and decode algorithm. The encode algorithm takes an input message of length k bits and outputs a code word y of length n bits. And we can assume that the encode algorithm is randomized. The decode algorithm takes in a tampered code word y tilde of length n bits, and it's going to output some k-bit message. And in some of the results I'm going to talk about today, we may allow the decode algorithm to also be randomized. And we have the natural definition of correctness. So if you decode a valid encoding of a message X, then you should recover X with probability 1. So now let's look at the definition of non-malleability. So what does it mean for ENC-DEC to be non-malleable? So we're going to consider two experiments, a real experiment and a simulated experiment. So in the real experiment, we just do the natural thing. We take the message X, we run the encode algorithm, we apply the tampering function, we run the decode algorithm, and then we output X tilde. In the simulated experiment, we have a simulator which makes a draw from a distribution df, which is a distribution over a special string, same, and constant c. And this distribution df is allowed to depend on the tampering function f, but it cannot depend on the message X. So the simulator makes a draw from this distribution and outputs either the special string same or some constant c. If the simulator outputs same, the experiment will automatically replace that with the original message X. And otherwise, the experiment will output the constant c. Okay, and non-malleability requires that these two experiments are indistinguishable. So the intuition behind this experiment is that the simulator has to somehow simulate the effects of the real experiment while knowing the tampering function f, but without knowing the message x. So a really nice alternative definition was given by Agarwal et al. So this is equivalent to the previous definition, but kind of another way of looking at things. So we still have two experiments here. The first experiment stays the same. This is the real experiment. And now this equivalent definition says that ENC-DEC is non-malleable if the effects of this blue box, which consists of applying ENC, applying F, and applying DEC, can be simulated by sampling a function little g from df, where df is a distribution over the identity and constant functions, and then outputting g of x. Okay, so we can simulate the effects of the tampering experiment by drawing a function g from a distribution over identity and constant functions. Okay, and this definition is equivalent to the previous one. So it turns out that this definition is really nice because it can now be generalized to a notion called a non-malleable reduction from a class F to a class G. And again, this was introduced by Agarwal et al. So again, we have the same real experiment, but now we're going to say that the effects of this blue box can be simulated by sampling a function g from a distribution dfg, which is now a distribution over functions in the class g. So before we had a distribution over identity and constant functions, now we're allowing a distribution over functions in g. Okay, and at the end of the experiment, we output g of x. So the first thing that we can clearly see is that if we have a non-malleable reduction from the class F to the class that contains identity and constant functions, then we have a non-malleable code, just by the definition that we gave. And another nice property is that non-malleable reductions compose. So if we have a non-malleable reduction from the class F to the class G, and a non-malleable reduction from G to H, then we can compose the two encode and the two decode functions in order to get a non-malleable reduction from F to H. So how can we see this? So we can draw these boxes as before. So we start out with the real experiment over here, just with the encode and decode functions composed. And now we can replace the first blue. So given our non-malleable reduction from F to G, we can replace the first blue box with a distribution over functions in the class G. And now we can replace the outer blue, for every little g, we can replace the outer blue box with a distribution over functions in H. And now we see that the top and bottom are still indistinguishable. And so now we've been able to replace the entire outer box here with a distribution over functions in H. So given these nice properties, the approach that we're going to do is we're going to get a sequence of non-malleable reductions from class F1 to F2 all the way to FL. F1 is going to be our target class. So in this case, it's the class AC0. And FL is going to consist only of identity and constant functions. Using the composition theorem, we get a non-malleable reduction from F1 to FL. And this implies that we get a non-malleable code for F1. So I guess I can stop for questions.
Stefan.
Yes, there is a question.
Okay, I'm looking at.
Yes.
Right. So
yes, is
the
parity
number.
outside the purple region? That was a question from Gilles.
Yes, the parity is outside. So I think the purple region corresponded to the follow-up result of Ball, Go, and Wix. So yes, parity is outside that box. So that's kind of all of our techniques kind of rely on the same type of techniques that are used to show that parity is not an AC0. And I mean, that work was not my work, but it uses similar techniques. And the ban on the number of compositions, well, so the error when you, these indistinguishability, there's some error associated with them. So that's going to add up. So you can handle a polynomial number. If your error is negligible, you can handle a polynomial number of compositions. Okay, so let me continue. So the outline of what we're going to do is we're going to have a sequence of non-nullable reductions. So we know that we have prior work that constructed non-nullable codes for split state. And then we're going to consider two different types of local functions that I'll describe more later and show non-nullable reduction from these classes to split state. And then finally, we're going to show a non-nullable reduction from AC0 to this type of local function class. And the lines highlighted in red are the ones that I'm going to look at in more depth. Oops. Okay, so let me first discuss more formally what split state is and also discuss the prior work. Okay, so I'm going to be focusing on two split state functions. They can be generalized to more split state, but here the code word is going to be split into two parts, L and R. The tampering function G is also going to have two parts, G1 and G2. And now to apply the tampering function, we will just apply G1 to L and G2 to R independently. And the idea here is that the two functions are going to act independently on the left and the right part of the encoding. So there's a long line of work on non-nullable codes for split state, starting with constructions for single bit messages, then extending to multi-bit messages, and finally improving the rate where the goal is to finally get constant rate split state non-nullable codes. So now that we know about split state functions, I'm going to talk about the non-nullable reduction from local functions to split state functions. So let me start talking about different types of local functions. So we're going to have output local functions and input local functions. So for output local functions, we're going to define what it means to be output local. So we're going to look at the circuit representation of the function f. And then we're going to draw a graph with edges from inputs to outputs. And there's going to be an edge from input bit xi to output bit yj if the circuit for f contains a path from xi to yj. Okay, and something is going to be in local LO if the in degree, so each of these output bits has in degree at most LO. So the number of edges coming in is at most LO. And semantically, what this means is that each output bit depends on at most LO input bits. So it turns out that output local functions are already interesting for one reason, because they contain the class NC0, which is one of the class that we're interested in. In fact, local LO contains fan-in-2 circuits of depth log LO. And so for any super constant LO, local LO will contain NC0. So the result I'm going to show is actually an intermediate result. So here we're also going to restrict the functions to be input local. So again, we consider the same graph. And now a function f is going to be in local Li if the out degree, so now we look at the out degree of the input nodes, and the out degree of each input node should be at most Li. And semantically, this means that each input bit affects at most Li output bits. Okay, and then if we want something that is both input local with locality Li, output local with locality Lo, we just take the intersection of these two classes. Okay, so now I can state the first subresult. We showed in our work that when you set Lo and Li to square root of n, so input and output locality are square root of n, there is a non-malleable reduction from local to split state with inputs of length k and outputs of length k squared. Okay, so let's try to get some idea for how we can kind of leverage split state in order to get a result for local. So what I've drawn here is the real experiment. So in the real experiment, we get a split state code word, LR, and we're going to apply E prime, which is also split state. This is the non-malleable reduction for local to split state. And then we're going to apply the tampering function over here. And then we'll apply the decode function, D prime, which is also split state. And we will get L tilde and R tilde. And in order to give a non-malleable reduction by the definition that we saw for non-malleable reduction, what we need to do is we need to provide a distribution over split state functions such that when you apply this split state function to LR, you get something that is close to L tilde R tilde. So we need to simulate the effects of the real experiment using a split state function drawn from some distribution. So how are we going to do this? So the first thing to note is that our tampering experiment is itself already somewhat close to a split state function. Most of the functions here are acting either only on the left or only on the right. The only thing that's messing us up is these crossover edges from right to left and from left to right. And so what we want to show is that we can actually sample the values of these crossover edges. So the value of the nodes that these edges are adjacent to, we can sample them from a distribution that is independent. So the right to left crossover edges can be sampled from a distribution independent of R. The left to right edges sampled from a distribution independent of L. And once we've fixed these values, then we can view the entire tampering experiment as a split state function in L and R, which is our goal. So the distribution over functions comes from choosing these edges from a distribution. Once we do that, we have a split state function. Okay, so let's first look at the case of the edges that are crossing from right to left. So in this case, we're going to play a trick where we're going to increase the size of the right side. So make the right side a lot larger than the left side. And because we know that our tampering function is output local, we can bound the number of these red edges crossing from right to left by the size of the left-hand side, so the number of bits over here, times LO. That's due to the output locality. And we're going to set our parameters such that the size of the left-hand side times LO is a lot smaller than the size of the right-hand side. So why is this useful for us? Well, we're going to use a special encoding, E prime R, D prime R, which is a reconstructible probabilistic encoding. So it's an error correcting code, which has some additional properties. And the additional property is that for constant C, any C fraction of bits of the code word are uniformly distributed and do not depend on the encoded message. This type of encoding also has another property, which is why it's called reconstructible, but that is only comes up in the proof, so I'm not going to discuss that. So why is this useful for us? So remember that we said that the size of the left-hand side times LO is a lot smaller than the size of the right-hand side. So as long as the size of the left-hand side times LO is less than C times the size of the right-hand side, then we can actually simulate all the edges going from right to left just by setting these values uniformly at random. That's the property that this code gives us. Okay, so we've successfully handled the edges going from right to left. What about the values going from left to right? So now the strategy from before is going to fail. So we can only use our trick once. So we made the right-hand side larger than the left-hand side to deal with the first one, but we can't keep doing this. So we can't solve this in the same way as before. So how are we going to deal with this problem? So the first thing that we're going to do is we're going to make use of our second assumption, which is the bounded input locality, Li. So what that means is that for the number of edges going from the left to the right is going to be at most Li times the size of the left-hand side. And remember, since the right-hand side is a lot bigger than the left-hand side, what this means is that there are many positions on the right-hand side that are safe. So what does it mean by safe? It means that for many positions on the right-hand side, there are actually no incoming edges. And so we can figure out the value of these positions just using a split state function that depends only on R and not on L. So the idea would be is that when we decode, when we apply d prime R, we only decode based on the safe locations. We ignore the other locations. We only decode based on the safe locations. And now we can represent decode as the decode of the tampered code word as a split state function that depends only on R. So the problem, of course, with this approach is that if your decode function cannot adaptively depend on a tampering function. So we need to construct a single non-malleable code or non-malleable reduction E prime dr that works for every tampering function. We can't first fix the tampering function and then choose a d prime that works for that tampering function. So this doesn't quite work. So how are we going to solve this problem? So the solution is going to be to switch from a real decode to a simulated decode. So the actual non-malleable reduction will use a decode function that does not depend on the tampering function. Simulated decode will depend on the tampering function. And we're going to show that we can maintain consistency between the two, so the two experiments will be indistinguishable by doing a small number of consistency checks, which will ensure that we get the same output from the real decode and the simulated decode. And this is actually similar to techniques that we used in a much older work from 2008 on non-malleable encryption. Okay, so just to review what the real decode and simulated decode will do. So the real decode is going to reconstruct the nearest code word W real to W prime using everything, using all the blue locations. So that's the natural thing to do. It will use all the information that it has in order to decode. And then it's going to do these random consistency checks at the green locations to check that the nearest code word W real agrees with W prime. And the key is going to be that we only have to do a small number of consistency checks in order to ensure that W real and W prime are very close to each other. In the simulated decode, we are only going to use the orange locations, which are the safe locations that have no incoming edges from the left, in order to reconstruct WSIM. And these blue locations that have incoming edges, we're just going to treat them as errors, and we'll tolerate them because we are an error correcting code. And we are again going to check that WSIM agrees with W prime at randomly chosen green locations. And note that the green locations that are chosen may not be safe. So green locations may have incoming edges from the left. However, there's only a small number of green locations. So how do we simulate? How do we simulate D double prime? So note that the values at the orange locations depend only on the right-hand side. They don't depend on the left-hand side. So this is good. This is already split state. And the green locations may depend on the left-hand side, but we're going to set the parameters so that the number of green locations times L0 is at most C times the size of left-hand side. And so by the properties of the RPE, this means that we can actually leak this information. And so here we're again using the bounded output locality to say that there's only a small number of locations that we need to open on the left-hand side. And so we can just simulate all the information needed for the green locations. Okay, so now we've chosen the values of the right to left crossover edges uniformly at random. We've chosen the values of the left to right crossover edges to green locations uniformly at random. And once these are fixed, we can express L tilde and R tilde as a split state function of L and R by using the alternate decoding function D double prime. Okay, so I'll take questions again at this point.
I don't see any questions.
Okay.
Let's maybe wait for 3 more seconds. Okay, I think you can go ahead.
Okay, so there's one missing step in this sequence that I see there's one question actually that just popped.
Yes, there is one question from Machi. So do you decode from green only?
We decode from safe positions and green in the simulated decode. So anything that's a safe position, it doesn't have an edge at all, or green, which may have an edge, those are the only ones used in decode, in simulated decode. Okay, so let me move on. So there's one step that was skipped, so that I'm not going to show in this talk. So going from input-output local to output local. So this is possible to do. I'm not going to go into the details. And I also want to mention that the construction that I presented has a randomized decode algorithm. So the green positions are chosen at random. They're different each time you run decode. But you can also get rid of that assumption as well. And the original work as well as other works were able to get deterministic constructions for output local tampering. So I want to move on to the last part of the talk, which is the non-malleable reduction from AC0 to local. Okay, so in this work, we showed that for AC0 circuits of depth at most log n over log n and size at most n to the log n, there is a non-malleable reduction with input length k and output length k to the 1 plus epsilon from AC0 to leaky local. So I won't really talk about leaky local. It means that we're also allowed to leak some bits of the code word from the local non-malleable code. Okay, and this is an output local non-malleable code with locality k to the little o of 1. So the actual construction is a recursive construction, and each level of the recursion is going to correspond to a different non-malleable reduction that reduces the depth of the tampering circuit by 1. So this has to be done log n over log n number of times in order to get the full construction. And I'm only going to be talking here about the bottom level. So the bottom level is going to be the reduction from depth to circuits, which are CNF and DNF. So an OR of ANDs or an AND of ORs to the leaky local class of functions. So let me mention the high level ingredients. So we're going to use the local non-malleable code that I mentioned from previous work with n to the epsilon output locality. And we're going to be using the RPE again that we had before. So remember, this is just an encoding that remains private, so it doesn't leak any information about the message, given any C fraction size subset of the code word bits for constant C. And the other high level ingredients that we're going to use, so this is what I kind of alluded to. So these are ingredients that are also present in the proof that parity is not contained in AC0. So we're going to use a variation of the switching lemma of Hastad. So the switching lemma says that if you take a T width, CNF or DNF, so this is a depth 2 circuit, with the number of variables in each term is at most T, and you hit it with a random restriction. So I'm going to talk more about what a random restriction is, but basically you're going to set some of the input bits to 0 or 1 at random. So if you hit a CNF or a DNF with this random restriction, then you're going to collapse to a T depth decision tree. And here we should think of T as epsilon times log n. So this is what a decision tree looks like. So at each step, you look at a different variable, and then if it's 0 or 1, you go right or left, and you proceed through the tree. At the bottom, you output either 0 or 1. For each path, you have a different output. And the main thing to notice is that decision trees of depth epsilon times log n are actually n to the epsilon local functions. And the reason for that is that if it has depth epsilon times log n, since it's a binary tree, the number of nodes in this tree is going to be at most n to the epsilon, which means that we only ever look at n to the epsilon variables. So this decision tree is also a local function. And in fact, we're not going to use the switching lemma itself. We're going to use a pseudorandom version. So pseudorandom switching lemma. So Trebizond and Shu proved that the switching lemma still holds when the random restriction that we hit the CNF or DNF with is sigma-wise independent. So let's look at more closely at what these random restrictions are. So the random restriction is going to have some parameter P. And this P is going to be the probability that, so we're going to go bit by bit. With probability P, we're going to choose that location to be a star. That means we leave it alone. It means we don't change the variable in that position. And with probability 1 minus P, we're going to set it to 0 or 1 at random. Okay, and this is a random restriction with parameter P. We can view this restriction in another way, which is equivalent. And the other way we can view it is that we kind of first sample all of the randomness, and then we apply a deterministic function to the input. So we're going to first sample a set S of random locations using randomness R, and these are the locations where we're going to put stars. And we're also going to sample a 0, 1 vector with randomness R prime. So these are the 0, 1s that will go in the non-star positions. And then we just go bit by bit. And if we're at the ith bit and I is not in the set S, we're going to set it to the next random value. And if I is in S, we're going to set it to star. Okay, so now we can see what a pseudorandom restriction is. So in a pseudorandom restriction, we want to take the second view of how to sample a random restriction. And it's going to be sampled in the same way as we do before, except that before R and R prime, the randomness for sampling the set and the values of 0, 1 were uniform random, but now we're going to choose R and R prime so that they're not uniform random, they're only sigma-wise independent. And this means that we can generate R and R prime using a short seed zeta. Okay, and then as before, we're going to sample a set of locations and sample values using these sigma-wise independent randomness R and R prime. Okay, so now let's see what's going to happen. Let's try to actually get our non-malleable reduction. So in the first attempt, we're going to not even use the pseudorandom restriction. We're just going to try to use a random restriction and see what happens. Okay, so we're going to first encode our message using our local non-malleable code. And we're going to get a code word X, which has bits X1 to XK. And then when we run our non-malleable reduction, the encode of the non-malleable reduction is going to simulate a random restriction where each star position of the random restriction is going to be replaced with one of the bits of this encoding, and the random 0, 1 positions will just be set to 0 or 1 at random. Okay, so the encode algorithm of the non-malleable reduction is essentially simulating a random restriction. It puts code word bits in star locations, and it puts 0, 1s in the other locations. Okay, and now this is a picture of the tampering experiment. So this box here is a very complicated CNF or DNF, where all the output positions depend on all the input positions. But because of the switching lemma, we know that when we apply this, essentially apply this random restriction during encode, what's going to happen is that this complicated CNF or DNF is going to collapse into these local functions. Okay, and this seems very useful because now we have a non-malleable code for local functions. So it seems like we have a non-malleable reduction. But there's still a problem with this construction, and that is that now we don't know which bits to decode. So remember, the star positions are the positions that contain important information about the code word. The other positions are just random 0, 1 bits. But now we've lost this information. It was used during encode, but we've lost it during decode, and we don't know how to decode this. We don't know which positions are relevant and which positions are just random 0, 1 values. So the solution is going to be to use a pseudorandom restriction instead of a random restriction. So now what we're going to do is we're going to run the local encoding algorithm to generate the code word X, which has bits X1 to XK. And we're also going to choose zeta, which is the seed for the pseudorandom restriction of the switching lemma, of the pseudorandom switching lemma. And we're going to encode this seed using an RPE. And we get R1 to Rm. And now we're going to append these values R1 to Rm to the code word. And now when we encode, we're going to use zeta in order to generate the pseudorandom restriction. Again, we're going to place the X1 to XK values in the star positions. The other positions are going to be 0, 1 at random. Okay, and now we have what we need to apply the pseudorandom switching lemma because the blue positions are sigma-wise independent because of how we chose the parameters for the pseudorandom switching lemma. And R1 to Rm are also sigma-wise independent because this is a property of the RPE, which says that any constant number of positions are uniform random. So now we can again apply the pseudorandom switching lemma, and now we collapse down to these local functions. And finally, we can now simulate everything So how will we simulate the effects of the tampering function using local tampering? So in the simulation, we're going to choose the seed zeta, and we're going to choose random values for the yellow positions. We're going to fully compute the values of the green output positions using the same trick as before. Because we have good output locality, we can afford to leak all of the input bits because there's only a small number of green positions. Once we learn this, we learn the tampered seed zeta, which allows us to figure out which positions are the star positions. So the red positions are the star positions. They're the ones that we care about. And now we have a local tampering functions with the correct size input and the correct size output. So the local tampering function that we've reduced to is the local function that is restricted to the gray inputs and the red outputs. And that is the non-nullable reduction to local. So I just want to end with, so I guess let me just take questions if there's any question and then wrap up.
Are there any questions now? Let's wait because maybe someone is typing. Okay, I think there are no questions. You can go ahead.
Okay. So I just wanted to end with some discussion and open questions of kind of what are the interesting things left to do in this regime. So I think the obvious question is, can we get non-nullable codes for more types of tampering classes? So note that, as I mentioned before, anything that's kind of beyond AC0 is going to require some kind of computational assumptions if we want encode and decode to be efficient. And that's because for classes beyond AC0, we don't know how to separate them from P. And I also just wanted to mention a late breaking result, which was just submitted to ePrint. It's either already there or will be live in a few days, which is together with Ilan Komargatsky and Rafael Paz. And this result achieves non-nullable codes for all polynomial size tampering circuits with bounded polynomial depth and no CRS, but it does need computational assumptions, some of them pretty strong. And so in general, it's interesting to see, we need some computational assumptions, but can we get non-nullable codes for larger classes of tampering functions with kind of minimal computational assumptions? And since this is ITC, Information-Theoretic Cryptography, I also wanted to mention the question of obtaining non-nullable extractors for these various types of complexity classes. So non-nullable extractors are similar to non-nullable codes. They actually imply non-nullable codes, but the parameters of the non-nullable extractor will affect the parameters of the non-nullable code. So for example, for AC0, the result of Chattopadhyay and Lee achieved their non-nullable codes for AC0 going through a non-nullable extractor, but the parameters are not optimal. And for some of the other complexity classes, we also do not know of non-nullable extractors for these classes. And I also want to mention that the recent result of non-nullable codes for bounded degree polynomials also goes through a construction of non-nullable extractors and then uses that to get non-nullable codes. And then finally, the last question that I wanted to mention is finding applications of these types of non-nullable codes, so non-nullable codes for various complexity classes, to other areas of cryptography. So kind of what can they be useful for in cryptography other than tamper-resilient cryptography? So there has been quite a bit of success in applying bitwise or split-state non-nullable codes to obtain improved constructions of non-nullable encryption and non-nullable commitment But as far as I know, there haven't been similar results for these complexity class non-malleable codes. So with that, I guess I'll end, and I'm happy to take any questions.
Okay, so let's thank Dana. Are there any questions?
I have a question if we're waiting for people to formulate questions in the Q&A.
Sure.
So what are, in terms of places where we know non-explicit, like say probabilistic constructions versus, settings, but where we don't have like explicit constructions?
Mm-hmm.
Are there, what are the, where are the kind of big open questions there? So I recall this work of, Chiragchi and Guruswamy and maybe some others that you mentioned that showed some basic existential results also.
Right.
What the, what the state is there.
Right. So if you just want existence results, we kind of know it for very, very large classes of tampering functions. So as long as the class is kind of slightly smaller than the total possible number of tampering functions, then we can get these existential results. I think the ones you're referring to are for bounded polynomial size tampering. So there's also randomized constructions, but they can be kind of de-randomized using a CRS. So we have so there are constructions known for polynomial bound tampering in the CRS model, and we had some follow-up work with that, which does not require CRS but has computational assumptions. So yeah, I guess that's a good question. I don't know if there's any reason to think that that it would be impossible to get information-theoretic non-malleable codes without CRS for bounded polynomial tampering. So maybe others can speak up if they know a reason why that should be impossible, but I guess that would be a huge question.
Thanks. Anat has a question. Maybe she could speak up.
Yes. Yes, I should. How do I do it?
You can unmute herself.
She can unmute herself. Okay. Anat. Okay. Ask to unmute. Maybe I can
unmute. Yeah.
Okay.
Can you hear me? Yeah. For some reason, it's working for me. Okay, good. So I was just wondering if there is some provable separation between the deterministic decoding and the randomized decoding model.
Yeah, that's a great question. So actually, the original definition required the deterministic decoding. And I think for cases where you have encryption or where there's a secret key, it's kind of without loss of generality because you can use a PRF to simulate that randomness. We were actually not sure if they are equivalent for non-malleable codes, for the non-malleable code setting where there's no secret key. Our first construction used a randomized decode, but then we were able to remove this randomness and get a deterministic decoding. So I don't think we know any examples where the decode has to be randomized, but it could be possible to separate them.
I see. Okay, thanks.
Sure.
Okay, Maciej had a question, but now he wrote, "Forget my last question." So I guess we can forget it. Are there any more questions?
Because I have a sort of an open-ended question, but it seems like it's significantly harder to get non-malleable codes than it is to just proof circuit lower bounds or some sort of like come up with a function that cannot be computed in some class. But it seems like a necessary like prerequisite. You need to come with a function that the class cannot compute. Do you think that would be possible to somehow do it almost generically, like some generic idea to say if a class can't compute a function, you can also design a non-malleable code for that class? Or what's the main hurdle or difference between these two problems?
So I guess we do have a result that I didn't talk about. It's in the CRS model and computational assumptions, which kind of shows that classes for which we have average case hard problems, we can get non-malleable codes for. I mean, the formal result doesn't quite show that, but that's kind of the spirit of the result. But we also needed kind of additional stuff on top of that. I think the main issue is that hard problems kind of seem to give you some kind of secrecy, but it's not clear that they give you non-malleability. So going from like something that's hard to compute to some kind of non-malleability guarantee, it's not exactly clear how to do that. It's kind of a similar problem as like semantically secure encryption to non-malleable encryption. And that was kind of the ideas that we used in our result. But that required a CRS and computational assumptions.
Is there anything known for like space-bounded computation or other, classes that for which we do have like hardness results, and where the things that are hard for that class don't necessarily, like, they have to lie outside the class, obviously, but maybe they're hard and by going off in some different direction, like using a lot of space but not a lot of time or something like that.
Right. So we also had a result on space-bounded and streaming algorithms, which uses like some of Ron Raz's work on like computing parodies or learning parodies. And I think there's also work on space-bounded tampering in the random oracle model. But yeah, I think like any class that doesn't contain P is either provably or by conjecture is a good candidate for non-malleable codes.
I think Sebastian had some paper on this, right? Sebastian and his students had a paper on non-malleable codes in the space-bounded model.
Yes, I think I cited it on one of my slides, but I don't
yes, it was on your slides. Yes, are there any more questions? I hear some noise from Anat.
No, sorry, that was a door slamming.
Okay. Okay, so I guess there are no more questions. So let's thank Dana again.
Thank you.
And now we have a break, right? Or
I think we're done for today.
We're done for today. Okay, good.
Yeah, that was the last talk of today. Yeah. So we'll resume tomorrow.
That's right. So at 9 a.m. Eastern Daylight Time. So,
Great talks. Thank you so much.
Thanks a lot.
Thank you.
Thank you, everybody.
Thanks.
Bye-bye.
Bye.